Sleep and study. Don't forget to subscribe.
We started this chapter by considering quantum mechanics in 3 dimensions. The first tool we used to solve problems, to solve the time-independent Schrodinger equation in 3 dimensions in particular, was separation of variables. We used separation of variables back in 1 dimension as well to separate the time evolution of an equation from the spatial evolution. That was how we got the time-independent Schrodinger equation from the time-dependent Schrodinger equation. In the case of 3-dimensional space, we also use separation of variables to separate the dimensions of space from each other. X from Y from Z, or in the case of spherical coordinates, which are most convenient for spherically symmetric potentials like we have for the case of the hydrogen atom, R from theta from phi. Another major difference between 3-dimensional space and 1-dimensional space is that in 3-dimensional space we have angular momentum. Angular momentum is not something that's going to fit into a single dimension, of course. So let's think about how angular momentum might behave in quantum mechanics. The approach we're going to take in this lecture uses operator algebra, the same sort of cleverness that we used back when we were talking about the quantum harmonic oscillator in 1 dimension with raising and lowering operators. We're going to take a very similar approach here. Back to basics though, first let's consider angular momentum. Angular momentum is what you have when you have an object and it's rotating about some axis. In classical physics, you were used to thinking about this as something like r times m times v, the momentum and the radius, mvr. The best way of expressing this in classical physics is as L, which is a vector, is r vector cross with momentum vector, where r is the vector that goes from the axis to the object that's rotating, and p is the momentum, linear momentum, of the object that's rotating. We can make an analogous expression in quantum mechanics simply by replacing the arrows with hats. I know that's not terribly instructive, and we'll talk about that in more detail. But let's define a momentum operator, L hat, that's equal to r hat cross p hat, where p hat is a vector momentum operator and r hat is a vector position operator. Essentially, x hat, y hat, z hat as a vector crossed with px hat, py hat, pz hat, if I was writing things out in Cartesian coordinates. Now at this point I'm going to save myself a lot of writing and drop the hats. I'll try and make it clear as I write these things down what's an operator and what's not an operator, but for the most part in this lecture what I'm going to be working with are operators. This is an operator algebra lecture after all. So if you actually do the cross product between these x, y, and z operators, and these px, py, and pz operators, what you end up with is, well, you can do cross products, presumably. You end up with y hat pz, sorry, I was dropping the hats, wasn't I? Y pz minus z py, that's our x component. Z px minus x pz, that's our y component. And x py minus y px, that's our z component. Now these are all operators, and they're the same sort of thing that you're familiar with. Y, and I'll put the hat on in this case, is going to be y, the coordinate multiplied by something. Whatever the operator is acting on, y hat acting on that is just going to be y, the coordinate, times whatever it's acting on, the function in this case. Likewise, for instance, py hat is minus I h bar partial derivative with respect to y of whatever the operator is acting on. So these are the usual operators. We're just combining them in a new way, in 3 dimensions. Now, as far as answering the question of how angular momentum behaves, one of the interesting questions is it quantized, for instance? How should we describe it? The approach that we're going to take here is motivated by, for instance, when we were talking about the position operator, we considered the eigenstates of the position operator. Those were the Dirac delta functions. Those were useful. If you consider eigenfunctions of the momentum operator in 1 dimension, you get plane wave states, states with definite momentum. And of course, if we're considering eigenstates of the Hamiltonian, those are the stationary states. Whatever the operator, if we consider the states, the eigenstates of that operator, we get states with a definite value of the observable associated with that operator. This is especially interesting to do in the case of angular momentum. So, I said this was an operator algebra question. How can we analyze the algebraic structure of the angular momentum operators? Well, I said angular momentum operators there, and there are going to be three of them. I'm going to break it down into Lx, Ly, and Lz in Cartesian coordinates, because those are the coordinates that are most easy to work with. The way to think about these things in the operator algebra context is to think about commutators. And you'll see a very good example later on of why commutators are useful. But in this case, for instance, consider calculating the commutator of Lx and Ly. Now I know what the definitions of Lx and Ly are in terms of their Cartesian coordinates, so I can expand that out. Y pz minus z py, z px minus x pz. That's what I get for Lx, Ly. And from that, I'm going to subtract z px minus x pz and y pz minus z py. So this is Lx, Ly minus Ly, Lx, just by the definition of the commutator. If I expand out each of these terms, for instance, you'll get, if I expand the term from the product of these two terms in the expansion, I've got a y, I've got a z, I've got a pz, and I've got a px. All of these coordinates are in some sense different, except for pz and z. Back when we were talking about quantum mechanics in 3 dimensions, at the very beginning of this chapter, we talked about the commutators of, for instance, pz and z being the same sort of commutator as you calculated in 1 dimension between, say, x and px. Y and pz, however, commute, as do y and px, z and py, etc. If the momentum and the position operators that you're considering are not the same coordinate, for instance, if I'm not talking about x and px, y and py, z and pz, the operators commute. So when I calculate the product here, y pz times z px, I have to keep the relative order of pz and z constant, but I can move the px and the y around wherever I want. What you end up getting for that, then, is something like this. I'll start at the left. This is going to be a kind of long and annoying expression. Apologies in advance. We're going to get a y, px, pz, z. So y, and I have to keep the pz and the z in order, and I'll put the px on the right, for instance. Actually, you know what? I'll save a simplification step here. I'm going to move the px to the left because I can do that. Px commutes with pz and z, and just write pz, z. And I'll put parentheses around them to signify that I have to keep them together in that order. The next term I get, multiplying across here, I have a y, I have a pz, I have an x, and I have a pz. So I have a pz and a pz, and pz of course commutes with itself. It doesn't even matter the order that I write pz and itself. So for this term, I'm going to get something like minus y, x, and I'll write pz, pz, just writing it down twice. If I keep expanding out these terms, minus z, py, px. It's hard to read my notes here, since my handwriting on my notes is even messier than my handwriting on the screen. X, py, z, pz, in parentheses again, from the contribution of this term. Comes in with a plus sign because we have two minuses. The z and the x commute as needed, as does the py and the pz, but I have to keep the z and the pz in order, so I've got z, pz, x and py being pulled out front. That's for the top two terms here. For the bottom two terms, everything is going to have a relative minus sign. So I'm going to get a minus and y px, z pz, plus z py px, plus x y pz pz, minus x py, and then pz z. So these are all my operators that I get as a result of expanding this out, provided I've copied everything down correctly from my notes. Now, if I've done things right here, you notice I have a z, py, px here, and a minus z, py, px here. So these two terms cancel out. I have a x, y, pz, pz here, and a y, x, pz, pz here. But x and y commute, so these two terms are actually the same as well, and they also cancel out. Another thing to notice here is here I have y px on the left. These two terms both have y px on the left. And on the right, I have things that don't commute, pzz and zpz. So this term here, I'll write it in black, I can combine these together. I'm going to have a y px, and then a pzz minus a zpz. And you know what that is. That's the commutator of pz and z, the operators. I can make the same sort of simplification over here. I have an xpy on the left, and I have a commutator of pz and z over here on the right, plus xpy z pz commutator, coming from these two terms. Now you know what the commutator of pz and z is. The commutator of z and pz is I h bar. This is the reason we like commutators. Commutator-like expressions often appear in expressions like this and allow us to simplify things, in this case just down to a constant. So this guy is going to be I h bar, and this, which is the same commutator only with the order reversed, is going to be minus I h bar. You can easily verify for yourself that swapping the order of the arguments in a commutator gives you minus the original commutator. So what I'm going to get now, at the end of all this, is y, where'd it go? I have a minus I h bar and I have an I h bar here, so I'm going to factor that out, and I'm going to have a y px and an x py, which should start looking familiar. Y px and x py appears in LZ. So this overall expression is just going to be I h bar LZ. So we started out calculating the commutator of Lx and Ly, and we got I h bar Lz. You can write down expressions for all of the commutators in this way. The commutator of Lx and Ly is I h bar Lz. The commutator of Ly and Lz is I h bar Lx. And the commutator of Lz and Lx is I h bar Ly. Likewise, if you swap the orders, you get minus signs. These are the commutators that are going to be useful to us in considering the algebra of angular momentum. If you feel the need to memorize formulas like this, note that the order these expressions always come in is always sort of cyclic, always sort of alphabetical. X to y to z and back to x. Here I have x, y, z. Here I have y, z, x. Here I have z, x, y. Always going around in this sort of clockwise order. You see a lot of sort of cyclic or anti-cyclic sort of permutation type arguments associated with commutators like this, and this is the first time that this sort of thing has shown up. So one thing you notice right away is that Lx, L, and Ly don't commute. We didn't get 0 for the right-hand side here. What that means is that if you want to determine simultaneously Lx and Ly, you have to consider the uncertainty relation between Lx and Ly. If I want to simultaneously determine Lx and Ly, the generalized uncertainty principle from the last chapter tells me that the product of the uncertainties in Lx and Ly is going to be given by the commutator of Lx and Ly. And if you go back to the previous page and figure out what that expression actually looks like, you get h bar squared over 4 times the expected value of Lz squared. So if I have some angular momentum in the z direction, I cannot simultaneously determine Lx and Ly. What that means is that if I'm considering angular momentum, I shouldn't be thinking about the angular momentum in the x direction or the angular momentum in the y direction. They're not very convenient observables to work with. What is actually a convenient observable to work with is L squared, which is defined to be the sum Lx squared plus Ly squared plus Lz squared. Essentially, the squared magnitude of the angular momentum, if you wanted to think about this in the classical context. This is sort of like saying r squared is the total length of a vector. So, the question then is, how does this L squared work? One thing you can do with this, L squared, since we're calculating commutators, is ask what's the commutator of L squared with, for example, Lz. Can I simultaneously determine one of my angular momentum direction coefficients with this total angular momentum squared sort of operator? What is this commutator equal to? Well, This L is going to be Lx squared plus Ly squared plus Lz squared, and we can separate out those commutators. Lx squared commutator with Lz plus commutator Ly squared commutator with Lz. And the third term is commutator of Lz squared with Lz. Now the commutator of Lz squared with Lz is just going to be 0. This term drops out. This is going to be Lz, Lz, Lz minus Lz, Lz, Lz. These two commutators we have to treat in a little more detail. So let's expand them out. This is going to be Lx, Lx, Lz minus Lz, Lx, Lx. And this is going to be Ly, Ly, Lz minus Lz, Ly, Ly. You can simplify this expression by adding and subtracting the sort of missing terms. If you think about this, here I have two x's on the end and Lz. What about Lz in the middle? So let's add and subtract Lz in the middle here. I'll write this as minus Lx, Lz, Lx plus Lx, Lz, Lx. So I haven't actually changed this expression any, I've just added and subtracted the same quantity. In the operator case, the addition and subtraction gets a little bit more difficult to understand, but this is essentially an identity. And I can do the same sort of thing here. I'll write minus Ly, Lz, Ly plus Ly, Lz, Ly. Now this we can actually work with. If you notice, here I have an Lx on the left, and then an Lx, Lz minus Lz, Lx. So if I was treating these two terms just by themselves, I could factor out an Lz on the left, and I would be left with a commutator of Lx and Lz. That would end up looking like this. So this is still an equality. Lx on the left, and then Lx commutator with Lz accounts for this term. This term is accounted for in much the same way, except I have to factor an Lx out to the right. So this is going to give me an Lx, Lz commutator with an Lx on the right. I can make the same sort of simplifications over here for exactly the same reasons, and I end up with pulling the Ly out to the left, Ly commutator with Lz, and pulling the Ly off to the right, Ly commutator with Lz, Ly on the right. So, still equal to my original expression. I haven't really made very much progress, but I know what the commutators of Lx and Lz are, or Ly and Lz. Those were the commutators I calculated on the last page. So this does actually simplify things out. The commutator of Lx and Lz is minus I h bar Ly. So this whole thing is going to be Lx. I'll stop writing it in square brackets because it's not a commutator anymore. Minus I h bar Ly. What I get for this commutator is the same. It's going to be minus I h bar Ly Lx plus, over here I've got Ly on the left, and these commutators are in alphabetical order, so I'm just getting positive I h bar plus I h bar Ly. Now, oops, I forgot where to go. I forgot my operator. The commutator of Ly and Lz is not just I h bar, it's I h bar Lx plus I h bar Lx Ly. Now, if you notice here, here I have an Lx followed by an Ly. I have to keep these in the right order because they don't commute, but I have a minus I h bar Lx Ly. I can bring the minus I h bar out front. Here, I have an I h bar Lx Ly. So, minus I h bar Lx Ly plus I h bar Lx Ly. These two terms cancel out. These two terms, here I have an Ly Lx, here I have an Ly Lx. Here I have a minus I h bar, here I have a plus I h bar. These two terms commute, or cancel out as well. So essentially what we're left with here, since everything is canceled, is 0, which means that L squared does commute with Lz. L squared commutator with Lz is equal to 0. This is the result that we'd hoped for. It means that we don't have a generalized uncertainty relation between LZ and L squared, which means I can simultaneously determine both L squared and LZ. That means I can hope to find states that are both eigenstates of L squared and LZ. And that's really what we want. When we're done with this, we want something that's easy to work with, and eigenstates are especially easy to work with. So, we've worked out the general algebraic properties of angular momentum operators. And we've settled on working with this combination L squared and LZ. Those are operators that we can hope to work with. And what we're hoping to find are eigenstates, things that we can, most easily work with. So, how are we going to proceed? The way we're going to proceed is ladder operators. This is the same approach that we took back when we were doing the one-dimensional quantum harmonic oscillator. It was difficult to explain then, and it's difficult to explain now. Fundamentally, if we're working with L squared and LZ as our operators of interest, consider this just a definition. L plus or minus is equal to L sub x plus or minus I L sub y. These should look a little bit familiar, and we're in the end going to make the same sort of cleverness arguments that we made back when we were doing the quantum harmonic oscillator. But for now, let's just consider the properties of these L plus or minuses. We're doing algebra with operators, and we were calculating commutators. So let me ask you the question, what is LZ commutator with L plus or minus? Well, you can substitute in the definitions of LZ, L plus, and L minus. And since the commutator is linear, I can just split this up into two separate commutators. LZ commutator with Lx plus or minus I times LZ commutator with Ly. You know what both of these commutators are. We've already calculated them out. You get I h bar Ly plus or minus I times z and y here now are in the wrong order, so I'm actually going to get a minus I h bar Lx in this case. So this is our commutator, and if you simplify that down, you'll find that this is actually equal to plus or minus h bar L plus or minus. So calculating the commutator of LZ with L plus or minus gave me something relatively simple. It just gave me L plus or minus back. If I ask you the question, what is the commutator of L squared with L plus or minus? Again, you can expand out the definition of L plus or minus, L squared Lx plus or minus I times the commutator of L squared and Ly. But you know L squared commutes with Lx and L squared commutes with Ly. These are essentially the same as it commuted with Lz. So without even calculating anything here, we know the answer is 0. So this is the algebraic structure of these ladder operators. The key fact that I mentioned earlier is that what we're looking for are eigenstates of both of these operators simultaneously. Simultaneous eigenstates like that. Essentially, the question that we need to ask, then that we can use these ladder operators to answer, is if we have some state, and I'm just calling it f here, if L squared f is going to be given is an eigenvalue, if f is an eigenstate of L squared, it would have an eigenvalue lambda, for instance, and f is a simultaneous eigenstate of Lz, it would have an eigenvalue, for instance, mu. What about L plus or minus acting on f? Now the terminology here should be suggestive. I called these things ladder operators. Let's see what that actually gets us. First of all, consider L squared acting on this, L plus or minus f, acting on f. Well, you know that L plus or minus commutes with L squared, so I can write this as L plus or minus times L squared acting on f without changing anything. But L squared acting on f, I know what that is. It's just an eigenvalue multiplied by f. So this is L plus or minus times acting on lambda f. Lambda just being a constant can be pulled out front, so I've got lambda and then L plus or minus f. What this tells you is that L plus or minus f, if f is an eigenvalue, f is an eigenstate of L squared, L plus or minus f is also an eigenstate of L squared with the same eigenvalue. I can ask the same question of Lz, what does Lz do to this mysterious quantity L plus or minus acting on F? This is a little bit more complicated, and I can simplify it by rewriting it slightly. Let's say this is Lz, L plus or minus. Now I'll write this as minus L plus or minus Lz plus L plus or minus Lz. I've just added and subtracted the quantity, and you can see what I'm trying to do now. I'm trying to arrange things such that I get commutators, as well as things that I know, because this is all acting on F, and I know what Lz does to F. It just gives me an eigenvalue. So this is now going to be the commutator of Lz and L plus or minus acting on F, plus L plus or minus Lz acting on F. And I know what Lz does under these circumstances, since F is hypothetically an eigenstate of the Lz operator. It's just going to give me mu F back. This commutator, I also know how this behaves. This is Lz commutator with L plus or minus, which just gave me plus or minus h bar L plus or minus back. So overall, we're going to get plus or minus h bar L plus or minus acting on F plus mu L plus or minus acting on F. If I simplify that out, plus or minus h bar plus mu times L plus or minus acting on F. And again, what we got, L plus or minus, is still an if F is an eigenstate of Lz, L plus or minus F is also an eigenstate of Lz with a slightly different eigenvalue. L plus or minus acting on F was an eigenstate of L squared with the same eigenvalue, but for z, L sub z, we got a different eigenvalue. Notice specifically what this does. L plus or minus increases or decreases the eigenvalue of Lz. So if F is an eigenstate, L plus or minus acts to produce another eigenstate with a slightly increased or decreased eigenvalue in the case of Lz. And this increase goes with the plus, and the decrease goes with the minus. What this means is that we have a ladder of states. L squared, that's sort of like the total angular momentum. Lz, that's the z component. L plus or minus, then, changes Lz, essentially, but does not change L squared. Now, by saying something like changes Lz, what I really mean is that L plus or minus acting on an eigenstate of Lz gives you another eigenstate of Lz with a different eigenvalue. Likewise, if we have an eigenstate of L squared, L plus or minus gives you another eigenstate of L squared with the same eigenvalue. What this means is that if I apply L plus to an eigenstate of Lz, I'll get another eigenstate with an increased Lz. If I keep applying L plus over and over and over and over again, I'll keep increasing my Lz component. I can't possibly ever have an Lz component that's greater than the total angular momentum, though, which means we have to have a top. There must be a top. An uppermost state that I get by repeatedly applying L plus. In order for there to be a sort of termination to that sequence, there has to be a top state. And what I mean by that is that L plus, acting on this, and I'll call it Ft for F top, is equal to 0. This is the same as when we were working with the quantum harmonic oscillator and we applied the lowering operator, which gave us a state with lower and lower and lower and lower energy. As we keep applying it, if we're getting lower and lower and lower energy, there must be a bottom, there must be a lowest energy, there must be a lowest energy bound state in order to, enforce normalizability. So that lowest energy bound state had the same sort of expression. we applied an operator to it, in that case it was A minus, and we got 0. That was how we found our ground state. Here we're just working with the algebraic structure, and there are actually two ends in this case. We have a top, we also have to have a bottom. Since if I keep applying L minus over and over and over and over again, eventually I'll get a sufficiently large and negative angular momentum in the z direction that I'll start to exceed the total angular momentum, and that's going to be a problem as well. So there also must be some state that L minus acting on FB gives me 0. In order to get from FT to FB, I apply L minus. So I can lower my top state gradually, rung by rung by rung, getting all the way down to the bottom. So this is what I mean by there being some ladder of states. As far as working out what this ladder of states actually looks like and what the eigenvalues are, this is where we have to use an additional dosage of cleverness. We weren't done with cleverness when we were done with the one-dimensional quantum harmonic oscillator, unfortunately, and in this case, the approach is similar. What we're considering is the operators L squared and L sub z. When we were talking about the quantum harmonic oscillator, we were talking about the Hamiltonian operator, and we were able to express the Hamiltonian operator concisely in terms of the A plus and A minus, raising and lowering operators. In this case, we're able to express the total angular momentum squared operator concisely in terms of these L plus or minuses. So consider L plus or minus acting on L minus plus. What this is going to do should be reasonably clear if I lower and raise a state, or if I raise and lower a state first, depending on whether I'm going with the plus-minus combination or the minus-plus combination in the bottom. So let's consider what this looks like. L plus minus, L minus plus, as a combination of operators. I can express both of these in terms of Lx and Ly, Lx plus or minus I, Ly, and Lx minus or plus I, Ly. Simply, minus and plus, plus and minus. If I expand this out, I've got an Lx and an Lx, so I'm going to have an Lx squared. If I expand this term out, I've got a plus and a, sorry, I neglected to swap my order there. A plus and a minus, an I and an I. So I've got 1 minus if I choose the top signs, and I've got an I squared if I choose the top signs. So that's going to mean I have a plus sign, plus Ly squared. Or alternatively, if I choose the bottom signs, I still have a minus and a plus. So I'm still going to get plus Ly squared, whether I choose the top signs or I choose the bottom signs. The remaining cross terms have Lx's and Ly's in them, and you can probably see maybe we're moving towards a commutator here. In fact, we are. What you get is minus or plus I times L... Where did my notation go? Lx, Ly minus Ly, Lx. And this commutator, you know what that is. That's I, H bar, Lz. So what we've got is this strange product of our raising and lowering operators gives us something that looks like a big chunk of L squared. So I'm actually going to rewrite this as L squared minus Lz squared. This is a positive step because Lz is something that I'm interested in. So I've got two things that I'm interested in now, L squared and Lz, instead of the things that I didn't actually care all that much about, Lx and Ly. So if I continue to simplify this, L squared minus Lz squared minus or plus, and now I've got an I and an I, so I'm going to have a minus 1 from that, so I'm going to change this minus or plus to a plus or minus, H bar Lz. Since what I'm actually interested in here isn't this strange combination, it's this L squared, I'm going to rearrange this and write L squared is equal to L plus or minus L minus plus Lz squared minus or plus H bar Lz. This is the expression that's going to come in handy for when we're considering the total angular momentum, for instance. When we're considering those top rung and bottom rung equations. So we know we have this ladder of states, and we know what the L plus and minus operators do to states that are on that ladder, either the top state or the bottom state, or some state somewhere in between. We now also have this expression for L squared, which is going to come in handy. So now, having derived this, let's go consider what our top rung actually looks like. The top rung, since what we're considering now are simultaneous eigenstates of both L squared and Lz, I have the following. I have Lz ft is equal to some eigenvalue, and I'm going to write this as h bar L times ft. You'll see why I'm using the L in a moment. Since this is a simultaneous eigenstate of Lz and L squared, I also have L squared ft is equal to, and I'll just leave this one as lambda ft. I also have my condition that I'm working with the top state here, which was L plus acting on ft is equal to 0. So now let's consider L squared ft in more detail. I have that expression that I derived for L squared on the last page. And there were actually two expressions there. I'm going to flip back for a moment. I have a choice here. I can choose the plus-minus combination or the minus-plus combination. And since in this case I know that I'm dealing with ft, I'm going to choose the combination where the plus acts first, because I know what L plus does to ft. So I'm going to write this L squared ft using the L minus, say minus right plus, characteristic of Brandt, L minus L plus combination plus Lz squared plus h bar Lz, all acting on ft. So I've just taken the bottom sign from the expression on the previous page for L squared. Now I know all of the terms here. If I expand this out, I have L minus L plus ft plus Lz squared ft plus h bar Lz ft. This guy, L plus ft, that's 0. So this term drops out. Lz acting on ft, I can write this as Lz, Lz, ft. Then I know what each of those Lz's does, just gives me an h bar L. So this is going to give me an h bar squared L squared ft. And this, well, this is just 1, so this is just going to give me an h bar squared L ft. So if I simplify this, what I get is h bar squared L plus 1 ft. This should start looking a little bit familiar, especially this L plus 1 combination. What this tells us essentially is that the eigenvalue lambda of L squared in this case is h bar squared L plus 1. So it's given us a relationship between L, the eigenvalue of the top, the eigenvalue of Lz for the top rung case, and the overall eigenvalue, the eigenvalue of the overall L squared, sort of the total angular momentum operator. So that's our top rung. Now let's consider the bottom rung. What does the bottom rung give us? Well, as before, we're working with simultaneous eigenstates of both Lz and L squared. So I have Lz f bottom is h bar, and I'll call this L bar in keeping with Griffith's notation for the eigenvalue of Lz. Likewise, L squared fb is equal to, and I'll leave it as lambda. Now keep in mind this is a different lambda than the one we had before, since we're dealing with a different state. And finally, L minus fb has to be equal to 0. That's what we mean by calling this the bottom rung. Lowering it gives you 0. You can't get any lower. So I can ask the same question that I asked in the case of the top rung. What is L squared acting on this bottom rung case? Since I know what the lowering operator does to the bottom rung case, I'm going to use my expression for L squared from a few slides ago that uses the lowering operator first. So L squared fb, substituting in my expression L plus L minus now, instead of L minus L plus like we used in the case of the top rung, plus Lz squared minus h bar Lz fb. So that's our expression. And once again, I know what each of these terms does. if I expand this out, L plus L minus FB plus LZ squared FB minus H bar LZ FB. Now L minus FB, as before, this is 0, so this term drops out. This term, LZ squared FB, I know what LZ FB does. It gives me this H bar L bar. So I'm going to have H bar squared and L bar squared FB from that term. And here, again, minus H bar squared L bar FB. So when I simplify this down, I get a very similar looking expression. I get H bar squared times L bar plus 1, sorry, L bar minus 1 in this case, FB. This tells me that lambda, the eigenvalue in this case, is H bar squared L bar minus 1. So that's actually all we need. You know that since I have a different state, I might in principle have a different eigenvalue lambda here, but since we know that we're going to go from the bottom rung of our ladder to the top rung of our ladder and back by repeated applications of the L plus and L minus operators, which leave this eigenvalue unchanged, they don't affect the eigenvalue of L squared, what I'm going to get is the same eigenvalue. So this tells me that H bar squared L bar minus 1 has to be equal to H bar squared L plus 1. And that's actually the key, one of the key facts here. The structure of the eigenvalues we get here, as resulting from that, the L bar minus 1 equals L plus 1, the only way that this can be solved is if L bar is equal to minus L. If you substitute this into the original equation, you see it actually works. So if L bar is going to be minus L, that means we have the two ends of our ladder defined. Going from the bottom to the top, if I have LZ, the eigenvalue that I have for the bottom is going to be minus L H bar, and for the top is going to be L H bar. For the eigenvalue of L squared, then, what I'm going to get at the bottom is going to be H bar squared times, well, you know what's coming, L plus 1. And for the top, it's going to be the same, H bar squared L plus 1. And there are going to be some number of steps that I need to apply the L plus and L minus to go from either the top to the bottom or from the bottom to the top. So there are going to be, let's say, n steps. And this n, of course, has to be an integer. I can't apply an operator half of a time or 3/2 of a time. What that means is that L is going to be minus L plus n. The number of times I have to add H bar to minus L H bar to get L H bar. What that tells you is that L has to be that integer n divided by 2. So that's actually pretty much all you need to know. We have found our eigenvalues. L is going to be a half integer, so L is either going to be 0 or a half or 1 or 3/2, etc. And the eigenvalue for LZ is going to be something between minus L and L. If I write this as LZ acting on some state is m H bar times that state, m is going to be minus L up to L. Some number starting from minus L counting all the way up to L. This should look rather familiar. Back when we were talking about spherical harmonics, we ended up with a very similar structure for the allowed values of things which were incidentally called L and M. And it's not a coincidence. I didn't just choose the notation inconveniently. These are the same sort of numbers. But if you recall back to when we were talking about spherical harmonics, L had to be an integer. It was either 0 or 1 or 2 or 3. So in this case, we actually have these half-integer combinations, which are actually incredibly important for the concept of spin, which is going to end up being the next section. For now, to check your understanding, here are a couple of questions to consider to figure out whether or not you've really grokked the structure of these eigenvalues and what the ladder of states looks like. In the last lecture, we were able to, purely by examination of the structure of the angular momentum operators, derive the quantization properties of angular momentum in quantum mechanics. We were able to examine the commutators, manipulate the operators, and essentially derive the eigenvalues associated with the operators L squared and L sub z. That's nice, and it's very useful. The eigenstates associated with Hermitian operators in the Hilbert space have nice properties, but we don't actually know what those eigenstates look like. In order to get something easier to visualize, let's consider what the eigenfunctions are, trying to express the angular momentum operators as partial differential equations that we can solve with the techniques that we've been applying earlier in this chapter. The angular momentum operators that we were working with in the last lecture are expressed in Cartesian coordinates. This was very nice because the Cartesian form has this nice symmetry to it and we could calculate commutators easily. Just by manipulating these, we were able to derive expressions like the eigenfunctions of L squared had this sort of form. H bar squared L plus 1 was our eigenvalue. Likewise, for L sub z, we ended up with eigenvalues of the form m times some constant h bar. The L's that we got had to be half integers, either 0 or 1/2 or 1 or 3/2, etc. And the constants m that we got here had to be between minus L and L, going up in steps of 1. So our eigenvalue structure here, as I mentioned, doesn't tell us anything about the actual form of f. When we were working with the one-dimensional quantum harmonic oscillator, we were able to derive, for instance, the ground state by knowing that the lowering operator acting on the ground state gave us 0. That was a differential equation that we could work with since we knew differential forms for the lowering operator. We can do the same thing with the angular momentum operators, but in this case, it's more worthwhile to think more generally. So suppose we just have some general psi of r, theta, and phi. This is our wave function expressed in general polar coordinates, and it would be nice to know how our angular momentum operators act on this general wave function. If we can express our angular momentum operators in spherical coordinates, we can write down this sort of eigenvalue equation. It will then be a partial differential equation that we can solve, in general, for any value of L or M. Unfortunately, in this lecture, we run into some thorny notational issues. I like to use hats to designate operators. Griffiths, your textbook author, likes to leave the hats off when it's not ambiguous. This is one of those cases where it is ambiguous and I would like to use the hats, but unfortunately hats are also significant in other ways. In particular, hats in this section of the textbook mean unit vectors. So I'm going to try and follow Griffith's notation, and I'm going to try and point out where things are operators and where things are unit vectors. But in this case, in this lecture, if I write something like Lx, I mean the operator. And if I write something like r hat, I mean the unit vector. Like I said, I'll try and be clear about what I mean in each case. At any rate, our goal here is to come up with spherical coordinates expressions for the operators that we were working with when we were considering angular momentum operator algebra, L squared and L sub z. So first of all, let's consider just L in spherical coordinates. There's going to be a lot of math in this lecture, and I'm going to go through it only conceptually. The level of grunge in this sort of coordinate transformation is above and beyond what I would expect you to be able to do for an exam. So, most important, I need you to understand the overall structure, the sorts of manipulations that are being done. Change of variables in the context of partial differential equations is tricky, so let's try and just understand overall how it works. First of all, what we're working with is angular momentum, L, which is given by r cross p. Now I've left both vector hats and operator hats off of these, but this is the angular momentum operator, this is the position operator in spherical coordinates, and this is the momentum operator in spherical coordinates. The momentum operator in spherical coordinates is rather straightforward to write down. We can write it as minus I h bar times this gradient operator, del, which you know as, I'll write it in Cartesian coordinates, x hat times the partial derivative of x plus y hat times the partial derivative with respect to y plus z hat times the partial derivative with respect to z. You can apply this to an arbitrary function of x, y, and z, a scalar function, and it will give you a vector. So this is a vector, as is the momentum, so this is the sort of momentum vector operator. This gradient can be expressed in spherical coordinates as well, and expressed in spherical coordinates it has this partial derivative with respect to r, partial derivative with respect to theta, and with respect to phi. The partial derivatives with respect to theta and phi have to be rescaled, since, for instance, if you consider it in Cartesian coordinates, this is essentially a spatial rate of change. It's a vector that points in the direction that the function changes most quickly with respect to physical space. And a change with respect to theta is not a change with respect to physical space. R d theta is a motion in space, whereas r sine theta d phi is a motion in space. So these are our motions in space, and the rescaling necessary is taken care of by this 1 over r and this 1 over sine theta. This gradient gives us the momentum, which we can cross with the radius operator, the position operator in spherical coordinates, which is quite simply r hat. So this hat now designates a unit vector, and this designates a coordinate. And as usual, our position operator is multiplication by the coordinate in question of, well, the multiplication of this with whatever the operator is acting on, some function in this case. So our angular momentum then is going to be a cross product of something like, I don't know why I erased it, r hat. So I'm going to be taking the cross product of r hat, that's the vector part of my position operator, with this part of my momentum operator. I can pull my minus I h bar out, and this is what you end up with, simply taking cross products r cross theta, and r cross phi. Where here I had a 1 over r in my gradient, but it's been cancelled out by the r coordinate multiplication in my position operator. Likewise for phi. There was a 1 over r here as well. This can be simplified slightly. You know that r cross r is going to be 0. The cross product of any vector with itself is going to be 0, since the cross product depends on the angle between the vectors. They have to be pointing in different directions. R cross theta is going to give me phi hat, a unit vector pointing in the phi hat direction. And r cross phi is going to give me minus theta hat, a unit vector pointing in the minus theta direction. You can, therefore, you're only going to end up with two terms, and that will be our angular momentum operator. Since, however, what we were actually doing when we were working with L squared and Lz, we needed expressions, for instance, for things like L plus or minus. This L plus or minus was expressed in terms of Lx and Ly, so what we actually need to do is take the overall angular momentum operator in spherical coordinates and use it to find angular momentum operators in Cartesian coordinates expressed in spherical coordinates. Now this is a very strange way of saying things, but essentially what I want is the angular momentum about the x-axis, the x component of the angular momentum, but expressed still in spherical coordinates. The way to do that, and the way Griffiths uses at least, is to take this expression for the angular momentum operator, which has phi hat and theta hat in it, and express the phi hat and the theta hat in Cartesian coordinates. Those Cartesian coordinates values of theta hat and phi hat will depend on theta and phi, so we end up with this weird hybrid Cartesian spherical coordinate system. But doing so allows you to identify the x component of the angular momentum, y component, and z component. If you actually do that, substitute in phi hat in Cartesian coordinates, for instance. Phi hat in Cartesian coordinates, this weird Cartesian spherical coordinate system, is minus sine phi I hat plus cosine of theta j hat, where I hat and j hat now are Cartesian coordinate unit vectors. This would normally be written as x hat in a normal physics class, but of course we know x hat as the x component position operator, and we can't reuse that notation. You can see why I'm sort of glossing over the details of this. Actually doing it all out would require a fair number of slides and a good deal of your time. At any rate, substituting in this expression, for instance, for phi hat, and a similar expression for theta hat, you can identify the I hat component of L, the x component of the angular momentum. And when you do that, this is what you're left with. So the x component of the angular momentum has derivatives with respect to both theta and phi. Likewise for L sub y, the y component of the angular momentum. L sub z, however, only has derivatives with respect to phi, and this should make a fair amount of sense since z is special in spherical coordinates. Phi is the angle that rotates around the z-axis. So that's all well and good. We're starting to work our way towards expressions of the operators that we're actually interested in, L squared and L sub z. We have one for L sub z, but what about L squared? L squared, it turns out, is easy to express if you think about it in terms of the L plus or minus operators. This was the trick that we used back when we were doing operator algebra. L plus or minus, of course, is expressed in terms of Lx and Ly. But we have Lx and Ly now, so we're ready to go. L plus or minus being expressed in terms of Lx and Ly, going back to your notes from the lecture on the algebraic structure of the angular momentum operators, we can express L squared rather simply in terms of L plus and L minus. L plus and L minus being expressed in terms of Lx and Ly, we can make combinations of Lx and Ly. Multiplying those out is simply an exercise in calculus, multivariable calculus, taking partial derivatives, applying chain rules, etc. When you do all of that, evaluating this expression that we got from the algebraic structure of L squared in terms of L plus, L minus, and Lz squared and Lz, you can go and look that up in your notes, you end up with an expression for L squared. This should start looking reasonably familiar. What I really want to do here is write this into an eigenvalue problem by adding some arbitrary function f. This whole operator, acting on some function f, is going to be equal to, we know what the answer is from our consideration of operator algebra. It's going to be h bar squared L plus 1 times f. It's going to give us our original function back. So this right here, this is our partial differential equation that we can solve for f, where f now is a function of r, theta, and phi, and is going to essentially give us our wave function. We only have angular components here, so there isn't going to be any radial part. That should make a good amount of sense. Radial motion doesn't contribute any angular momentum. We can do something very similar for L sub z. L sub z acting on some arbitrary function, and L sub z we already had an expression for. It was minus I h bar partial derivative with respect to phi of f. We know what that's going to give us already as well, because we know the eigenvalue structure of L sub z as well. It's going to give you m times h bar f. Both of these are going to be then partial differential equations that we can solve. This tells us something about the eigenstates of L sub z. This tells you something about the eigenstates of L squared. And if you look at these equations, they should be familiar. These are the angular equations that we had earlier. These essentially gave us the YLM of theta and phi as their solution. So what we've shown here is that the eigenfunctions associated with the L squared and L sub z operators are exactly the spherical harmonics. The spherical harmonics were what we got from a spherically symmetric potential expressing the time-independent Schrodinger equation in spherical coordinates. And this should make a certain amount of sense, since what we're talking about now is angular momentum, and L squared, for instance, angular momentum squared, has to do with the rotational kinetic energy. So it ought to play some role in the time-independent Schrodinger equation, which tells us the energy of the stationary states. So if we have an eigenvalue of L squared, simultaneous eigenstates of L squared and Lz are exactly the spherical harmonics. There is a slight difference here, and it comes down to the value of L. Essentially, we have two classes of solutions here. We have half-integer L and integer L. Our consideration of spherical harmonics gave us only integer L, whereas, our consideration of wave functions, the solutions to these partial differential equations, give us spherical harmonics, which are only meaningful for integer L. Half-integer L doesn't really make any sense in the context of spherical harmonics, which means if what we're talking about is angular momentum of something like a physical particle, orbital angular momentum, rotational kinetic energy, essentially, we can't have half-integer L. But we do have these half-integer L solutions. If I'm talking about wave functions, I have to have YLMs for my solution. That means I have to have L being 0, 1, 2, etc. and M being, minus L up to L. If what I'm just talking about, though, is the algebra of things, then I don't really know what the solutions look like. But I can have L is 0 or half or 1 or 3/2. This is interesting. My M values are going to behave the same way, minus L going up to L. But these half-integer values of L, they're rather strange. They're going to behave in ways that are utterly unfamiliar if what you're used to thinking about are things that actually live in ordinary three-dimensional space. But these do actually happen to have physical reality, and it has to do not so much with orbital angular momentum, the motion of a particle around in an orbit, for instance, as they do with spin angular momentum, or at least that's the name quantum mechanists, I think? I don't think I should say quantum mechanic. Quantum mechanists say is associated with these half-integer values. They have physical meaning in the context of spin angular momentum. As an example of how these angular momentum structures can be useful, consider the rigid rotator. What I mean by that is, suppose I have two masses, both equal to mass m, separated by some distance a. And I put them on a rod of length a, and I spin them around. This is a, system that can in principle be treated with quantum mechanics. The only energy associated with this system is going to come from rotational kinetic energy, since the thing is not allowed to translate. I'm fixing it to rotate about the center here. So my Hamiltonian operator is going to essentially be the rotational kinetic energy, which is going to be L squared over 2 times the moment of inertia. This is the rotational analog of p squared over 2m. I have angular momentum squared divided by twice the moment of inertia, the rotational equivalent of the mass. Now, I suppose I should either erase the hat for my Hamiltonian operator or add a hat to my angular momentum operator. I said in this lecture I wasn't going to use hats to designate operators, so I'll erase it from the Hamiltonian. At any rate, you know how L squared behaves. The moment of inertia here, I, is going to be 2, since I have two masses, times mr squared, essentially, so the mass times the radius squared, which is going to be a over 2 squared. So this is going to be ma squared over 2 for my moment of inertia. The time-independent Schrödinger equation then becomes h times my wave function is e times my wave function. That's my original. When I substitute in the specific definition of the Hamiltonian here, I have L squared, my squared angular momentum operator, divided by twice my moment of inertia, which is just ma squared. I have an over 2 here, and I have a 2 here, and they cancel each other out. If this is going to be equal to L squared acting on psi is going to be equal to e times psi, ma squared here is a constant, I can rearrange this and write L squared psi is equal to ma squared e times psi. This now, this ma squared e, this is my eigenvalue of an eigenvalue problem with L squared in it. I know what those eigenvalues are. This is h bar squared L plus 1. That's my eigenvalue, the form of my eigenvalues of the L squared operator. So what that tells me is that ma squared e is equal to h bar squared L plus 1. And I can solve this for e easily. It tells me that e is equal to, an equal sign somewhere, h bar squared L plus 1 divided by ma squared. These are the allowed energies, the energies of the stationary states, for the rigid rotator. You can just as easily go through the same sorts of arguments and write down normalized wave functions for the rigid rotator. But essentially this is a very common structure that you're going to encounter in quantum mechanics. Angular momentum is, of course, a conserved quantity in classical physics, and it's a conserved quantity in quantum mechanics as well, which means it's interesting in a lot of respects. And the quantum mechanical structures you get, either if you're looking at something like a rigid rotator now, since we could actually write a real-world wave function for this, we're stuck with just spherical harmonics for the wave functions, integer values for L, and you're going to encounter this sort of expression a lot in quantum mechanics, especially if you go on to the upper levels. Think about for a moment what we've accomplished. Solely by messing with operators and solving partial differential equations as motivated by this original hypothesis of the time-dependent Schrodinger equation, we were able to determine conserved angular momentum structures. We're even able to predict that there's going to be something strange happening for half-integer values of L in these eigenvalue equations, and that's going to be the topic of the next section in the textbook, spin. The half-integers have a lot of strange properties associated with them. So that's where we are, and that's where we're going. The machinery of quantum mechanics is obviously very productive, and we're going to keep working our way through the results of it for the next couple of lectures. We've spent the last couple of lectures talking about angular momentum. From the quantum mechanics perspective, we ended up talking about a total angular momentum operator L squared and a z component of angular momentum operator L sub z. These two operators gave us a certain algebraic structure, and we ended up with quantum numbers L and m. The allowed values of L were either integers or half-integers. L could be 0, a half, 1, 3 halves, etc., going up to infinity in steps of a half, whereas m could only be in between minus L and L in steps of 1. These quantum numbers were interesting for a couple of perspectives. If we considered the motion of a particle, for instance, the electron orbiting the nucleus in the hydrogen atom, we only got integer values of L, 0, 1, 2, 3, etc. Whereas the algebraic structure of these operators allows for L equals a half or 3 halves, etc., going up in steps of a half. These half-integer values are essentially valid solutions. And that brings us to the topic of spin in quantum mechanics. Essentially, these half-integer values of L are perfectly valid physical solutions, and they have meaning. They're actually what we use to describe an intrinsic property of fundamental particles like electrons called their spin. Spin is essentially a property of the universe. That's just the way things are. I don't have a good answer for why does an electron have spin, but I can describe the spin of the electron, and I can describe it using the same language as we used when we were discussing angular momentum. So, angular momentum, we were working with equations like L squared F, and the eigenvalues we got for that were h bar squared L, L plus 1. Likewise, L sub z applied to F gave us eigenvalues of the form m h bar. Examining the algebraic structure of this gave us allowed values for the L quantum number of 0, or a half, or 1, or 3 halves, etc. These integer and half-integer values had different interpretations. If I look at just the integer values, those describe orbital angular momentum, the angular momentum of a particle as it moves in a circle around a focus, for instance, around a center. So now we're talking about particle motion. And we can write a wave function, psi, of, say, x, y, and z, or perhaps more accurately, r, theta, and phi, that has this property of orbital angular momentum. You know what the answers for this are already. We've discussed it in previous lectures. The wave functions with specific values of L squared and L sub z, the eigenfunctions of the L squared and L sub z operators, are the spherical harmonics. We're also allowed to have spin, angular momentum, with integer values, but spin is really more interesting when we're talking about the half-integers, 1 half, 3 halves, 5 halves, etc. I keep writing 3/3. I wonder why. Here, these half-integer cases don't have any nice wave function that we can express, so we're really only talking about spin under these circumstances. So, what exactly is this spin thing? I can't give you a good argument or a good answer for this other than saying this is essentially just a property of the universe. The name spin, at least, I can explain, and the name comes from a classical analogy. Suppose we have a positively charged nucleus and a negatively charged electron orbiting that nucleus. we are going to have orbital angular momentum associated with the motion of that electron, but there's also the possibility that the electron itself would be rotating, spinning on its axis, for instance. If you think about the Earth orbiting the Sun, the Earth both goes around the Sun and spins on its axis. And that combined spin and orbit means there are essentially two distinct types of angular momentum in the context of the Earth orbiting the Sun. By analogy, there are two distinct types of angular momentum associated with a fundamental particle like an electron and a hydrogen atom. The electron moves around the nucleus, carrying orbital angular momentum, and the electron also, for some strange reason, also seems to have a spin angular momentum. And I feel compelled to put this whole picture in essentially finger quotes, because this is not a particularly rigorous definition of spin, only a very hand-waving analogy for what spin might mean. This doesn't make a lot of sense physically, because the electron, as far as we know it, is, first of all, described by the wave function, which tells us pretty much everything there is to know. And second of all, if we were going to say the electron is a particle, it's a point particle. And point particles can't possibly spin. They have no radius. What does it mean for an electron to spin? Well, one thing I can tell you is that if you have an electron, it actually produces a magnetic field. It has a magnetic dipole moment, which would lead it to produce a magnetic field. Just intrinsically, in and of itself, independent of any of its motion, an electron has a magnetic dipole moment. So that in and of itself hints that there's something more than meets the eye if we're just considering an electron, because a point charge couldn't possibly have a magnetic dipole moment either. These fundamental particles and their spin, really this is getting into the details of particle physics, but in particle physics, particles are divided up into two classes, fermions and bosons. And we'll talk more about what this means later on. It has really astonishing implications for whether or not particles play well with each other in some context. But fermions are particles with these half-integer spins, whereas bosons are particles with integer spins. Most of the particles you're probably familiar with, the electron, the proton, and the neutron, are fermions. Another particle that you're probably familiar with, the photon, the quantum mechanical particle of light, that thing that's emitted when a hydrogen atom undergoes a transition from, say, n equals 3 to n equals 2, is a boson. It has a quantum mechanical spin of 1, actually. Neutrinos, which we learned about a couple of lectures ago when we were talking about neutrino oscillations, are fermions. They have spin 1/2. Bosons, the W and the Z, these are particles that are associated with the weak nuclear force, the gluon being a particle that's associated with the strong nuclear force, and everyone's favorite particle these days, the Higgs. The Higgs boson has integer spin. There are other compound particles. Protons and neutrons are not simple discrete particles. Protons and neutrons are composed of quarks and gluons. Alpha particles and carbon-12 nuclei. These combined particles also have an overall spin associated with them. And you can imagine, since they're compound particles, their overall spin has a structure in and of itself. But you can, for instance, think about an alpha particle as having spin 0, or having spin 1, or having spin 2. So from the perspective of fundamental particle physics, spin is a really interesting thing and allows us to split things up into different groups, and we'll explain how those groups are different later on. From the perspective of this course, though, spin is essentially an operator algebra, the same as the angular momentum operator algebra. So all of these things are operators. S squared is an operator, S sub z is an operator, and these operators obey commutation relations the same as the commutation relations for angular momentum. So I'm not going to go through the derivations of why these things are the case. Essentially, these are operators that obey this commutation relation. This is a very strange statement to make, though, because when we talked about angular momentum commutation relations back in the context of orbital angular momentum, we wrote out differential operator expressions for S sub x. S sub z, for instance, had a partial derivative with respect to phi in it. S sub z, in this context, no longer has any partial derivatives in it, because this is now solely acting on these states. in the Hilbert space. And I'm writing them as kets now, S and M. S takes the place of the angular momentum quantum number, total angular momentum quantum number L, and M here, which is often written as M sub S, but I'm just going to write it M in keeping with the notation in the textbook, refers to the M counterpart in the spin operator algebra of the M quantum number in the angular momentum operator algebra. So these are the operator algebras we get, and the spin and S and M quantum numbers have the same sort of structure. S could be 0, or 1/2, or 1, or 3/2, etc. There's that 3/3 again. And I should really distinguish this as a lowercase s to distinguish it from the uppercase s's, which are operators. And M, the other quantum number, which can vary from -s up to s in steps of 1. So this is the spin setup that we're going to be working with. And believe it or not, this rather abstract mathematics actually makes testable real-world predictions. Most of those predictions come from the fact that this spin is associated with a magnetic dipole moment of a fundamental particle like an electron. And, well, we'll talk about that in a couple of lectures. For now, this is setting the stage for the mathematical structure of spin. Given the definition that we gave in the last lecture of spin as essentially an angular momentum operator algebra that doesn't actually have an obvious counterpart of particle motion, let's take a look at the operator algebra and the associated states, their eigenvalues, their eigenstates, etc., of the most basic case, the most basic non-trivial case, spin 1/2. Spin 1/2 is the system that you should think of if the quantum mechanical system you actually are trying to understand is too complicated. Spin 1/2 is about as simple as quantum mechanical systems get while still having rich behavior. So essentially what we're working with is S, which was our spin angular momentum counterpart for the L quantum number in orbital angular momentum of 1/2, which means we have an M counterpart in the spin angular momentum of either -1/2 or +1/2. So that's the structure of our system. We're working with two states. So S is 1/2, and our allowed values of M are then -1/2 and +1/2. The two states that we're working with then, I'm going to call them chi plus and chi minus. And what that means is that we're working with S is 1/2 and M is either +1/2 or -1/2. Another very common notation, and one that I'm going to use in this lecture, is to call the plus case up arrow and the minus case down arrow. So spin up and spin down. What's nice about this, the fact that we're working with a two-state system, is that no matter what our operator is, it's going to have a representation as a 2x2 matrix. The vectors that we're working with then, this chi plus, expressed in this basis, the basis of spin up and spin down, our chi plus vector, which I'm also writing as just up, is given by simply 1, 0. Likewise, chi minus, or spin down, is given by 0, 1. If these are the vectors that we're working with, what are the operators that we're working with? Our operators are going to be things that act on these two component vectors, so they're going to be 2x2 matrices. For instance, let's consider S squared. We know what S squared does from our consideration of the operator algebra. S squared, which is our counterpart for L squared, S squared, acting on the spin up case, is going to give us our eigenvalue, which was h bar squared s plus 1, and this is an eigenstate of s squared by construction. S, in this case, is 1/2, and if you plug this in, you find out this is equal to 3/4 h bar squared. We can use this sort of expression, which of course has a counterpart, s squared, acting on spin down. The spin down state is also an eigenstate of s squared, with the same eigenvalue, 3/4 h bar squared. I'm having trouble with my fractions today. 3/4 h bar squared spin down. These two, we can write those out in the matrix notation, not knowing what the operator s squared looks like, let's just write it as a, b, c, d, four unknown components in our vector. Spin up, we know what that looks like. That's 1, 0. And that's going to give us 3/4 h bar squared times our spin up, 1, 0. Likewise, we have our action of s squared on spin down, which we know about. Our unknown a, b, c, d matrix acting on 0, 1 gives us the same thing, 3/4 h bar squared, 0, 1. Now each of these we can expand out. We can do the matrix vector product here, and when we do, we get AC is equal to 3/4 h bar squared, 1, 0. Likewise here, we get BD is 3/4 h bar squared, 0, 1. This tells us that A is equal to 3/4 h bar squared, and that C is equal to 0. And this tells us correspondingly that B is equal to 0, and D is equal to 3/4 h bar squared. What that means is that our s squared operator expressed in this basis is 3/4 h bar squared, 0, 0, 3/4 h bar squared. And it's more conventional to factor this 3/4 h bar squared out front and just write this as 1, 0, 0, 1. The identity matrix, essentially. So this is our matrix representation of s squared. What other operators do we have to work with? The next one to consider is the other one where we have easy eigenvalues, s sub z. We know what s sub z does. Similarly, s sub z acting on our spin up ket gives us h bar over 2, our positive eigenvalue, times our upwards ket. Spin up ket. S sub z acting on spin down gives us minus h bar over 2 times our down ket. Similarly to the last slide, we can write out matrix representations of this. So some unknown a, b, c, d, and these are now different a, b, c, d from the last slide, acting on 1, 0 gives us h bar over 2, 1, 0, or a, b, c, d. Now these a, b, c, d's are the same as these a, b, c, d's, since we're considering the same operator. Acting on 0, 1 gives us minus h bar over 2, 0, 1. As before, you can do these matrix vector products and get AC is equal to h bar over 2, 1, 0, or B, not over, just BD in a column vector is equal to minus h bar over 2, 0, 1. Same sort of results. Fine. You find the same sort of results. A is h bar over 2, C is 0, B is 0, and D is minus h bar over 2. Which means we can write down our matrix expression for s sub z in this basis as simply h bar over 2 times 1, 0, 0, minus 1 for A, B, C, and D. So this is our expression for s sub z. We have s squared, we have s sub z. What about s sub x and s sub y, the other things that we might hope to one day observe, the spin, angular momentum, x component, or y component? Unfortunately, s sub x and s sub y are not terribly easy to evaluate on their own. So our starting point here is going to be s plus and s minus, the spin angular momentum equivalent of the raising and lowering operators. You can probably guess what sorts of equations we're going to use to determine s plus and s minus here. For instance, s plus, acting on the down state, gives us something proportional to the up state. I don't remember if we talked about this or not, but you can, by suitable analysis of the structure of these operators, determine what this proportionality constant is, and in this case it's h bar. Likewise, we know s plus acting on the up state isn't going to give us anything. We can't raise the up state any higher than it already is. This gives us 0. Similarly, s minus acting on the up state lowers down to the down state with the same proportionality constant, h bar, and s minus acting on the down state, we can't lower it any more than it already is, gives us 0. As before, you can write out matrix equations here. So say S plus. Suppose I write S plus as this unknown 2 by 2 matrix A, B, C, D. Acting on down, which is 0, 1, we get H bar times up, 1, 0. You're going to get two equations from this. You're going to get another two equations by knowing that S plus acting on up is 0, but I'll skip the details here. You can solve the system of equations that results here very easily, and what you find is that S plus, expressed in this basis, is given by H bar times 0, 1, 0, 0. The only non-zero component is the upper right. Likewise, expressing S minus as some unknown matrix, plugging in the definitions of the up and down kets expressed in this basis of up and down kets, you get a system of equations that you can very easily solve to find that S minus, expressed in this basis, is H bar times 0, 0, 1, 0. The only non-zero component is the lower right. You can start to get a feel already for the degree of symmetry that we're going to have when we're talking about the spin 1/2 system. Upper right, lower left. Diagonal identity, diagonal 1 and minus 1 for S sub z, for instance. These 2 by 2 matrices have a very nice, very symmetrical sort of structure. Now, knowing what S plus and S minus are, we can figure out what S sub x and S sub y are. Basically, if you remember, S plus was defined, the raising operator was defined in terms of the x and y component angular momentum operators. Likewise, S minus is given by Sx minus I Sy. These were our definitions, and these definitions carried over from the orbital angular momentum case, back when we were talking about a more general case, and we wrote L plus is equal to Lx plus I Ly. Same expression, I'm just using S instead of L, since I'm talking about a different form of angular momentum. Now you can treat these two equations naturally as a system of two equations and two unknowns that you can use to find Sx in terms of S plus and S minus, or Sy in terms of S plus and S minus, or you can simply look at the equations. If I told you that S sub x was equal to S plus plus S minus divided by 2, it shouldn't surprise you. If I add these two equations together, Sx plus Isy plus Sx minus Isy, the Isy parts are going to cancel out, and I'm going to be left with 2Sx. So I divide the overall result by 2, and I get Sx. Similarly, Sy, same sort of superposition, S plus minus S minus over 2I. S plus minus S minus is going to be Sx plus Isy minus Sx plus Isy. So my Isys combine, and I get 2 Isy, which I want to cancel out the 2I to get just Sy. So these are our operators. And now, knowing the matrix definitions of S plus and S minus from the previous slide, you can simply plug and chug. Sx, expressed in this basis, is H bar over 2, 0, 1, 1, 0. Sy, expressed in this basis, is H bar over 2, 0, minus I, 0. So these are our Sx and Sy. And now we know all of the operators. We have an expression for S squared, an expression for Sz, an expression for Sx, an expression for Sy, and of course, coming along for the ride, we have these S plus or minuses. These matrices go by a different name. They're called the Pauli spin matrices, for the most part. And I really struggle with the notation in an equation like this, because S is a vector, but I don't know whether to give it a hat, to call it an operator, to boldface it to give it an operator, or to put a vector arrow on top of it since it's a vector operator. So I'm just going to leave this as is. Context is usually enough to figure out what's an operator and what's not an operator, but you really have to keep in the back of your mind that sometimes these things are going to be confusing. So be very careful with the notation. Try to be as neat as possible with how you write these things down. It's very easy for a sigma to become an S, or a 2 to disappear, or a minus sign to become a plus sign, or an I to disappear. Keeping track of all of this requires a great deal of attention to detail, which is not something I'm very good at. I'll openly admit that. But while notationally speaking, this is a rather complicated expression, all we've really done is pull the h bar over 2 out of our expressions for the S sub x, S sub y, and S sub z operators. defining them as lowercase sigma sub x, sigma sub y, and sigma sub z operators, or matrices in this case, since we're working in the basis of the up and down S sub z eigenstates. So these are our Pauli spin matrices. The x component, for instance, S sub x, just to close the loop a little bit, is going to be h bar over 2 sigma sub x. Likewise, S sub y and S sub z, expressed in terms of these sigma sub x, sigma sub y, and sigma sub z. What's nice about this is it's relatively easy to manipulate. Like I said, this is about as easy as the math in quantum mechanics ever gets. The eigenstates of S sub x. Suppose we want to find the eigenstates of S sub x. That's a reasonable question. What does this state that has a definite value of the x component of the angular momentum actually look like? What we want under those circumstances is the eigenstate of S sub x. We want to know what the eigenvalues are. We want to know what the eigenstates are. Now we're working in this up-down basis. We have an expression for S sub x in this up-down basis. So h bar over 2, 0, 1, 1, 0, that was our expression. This is our sigma sub x. And our unknown vector, let's just call it xy. We don't know what the eigenstate is. We don't know what its components in this up-down basis are. Is equal to lambda xy. This is a 2 by 2 matrix eigenvalue problem. If you don't remember how to solve 2 by 2 matrix eigenvalue problems, I suggest you refer to the appendix in the book on linear algebra, or go back to our lectures where we did a very brief and unfortunately crappy review of linear algebra. I made those lectures at about 1 in the morning and I was running out of gas. The eigenvalue problem, just to review, you solve this system. Essentially, this only has a non-trivial solution if the determinant of this matrix, the net matrix here, moving this lambda times xy to the left-hand side of the equation, the determinant of that matrix has to be equal to 0 in order for it to have a non-trivial solution. So we want the determinant of the matrix, and I'll write it expanding the h bar over 2 into the matrix and subtracting the right-hand side off of this. We're going to have minus lambda h bar over 2 and then h bar over 2 and minus lambda for our diagonal components. We want the determinant of this matrix to be equal to 0. And that gives us our characteristic polynomial. The polynomial you get from the determinant of this matrix is very simple. Minus lambda times minus lambda minus h bar over 2 times h bar over 2. So we get lambda squared minus h bar squared over 4 is equal to 0. This is very easy to solve for lambda. We get lambda equals plus or minus h bar over 2. So those are our eigenvalues. This should not be terribly surprising. We chose the z component of the angular momentum more or less capriciously, so we should end up with the same sort of behavior if we had chosen the x component of the angular momentum. These eigenvalues now are the results that we would get for observations of a real physical quantity, the angular momentum, the x component of an angular momentum. So they can't really depend on the way we do the math. These are real sorts of physical things. So the fact that we get the same sort of results for the x component as we did for the z component shouldn't surprise you. Our x eigenvalues, or the eigenvalues for the x angular momentum operator, are plus or minus h bar over 2. Finding the eigenvectors associated with this is a matter of going back to the original equation, substituting in lambda, and solving the system of equations that results. I'm going to go back to this expression, which essentially this matrix multiplied by xy equals 0. That's the easiest way to get at these things. And if I substitute in plus or minus h bar over 2 into this sort of structure, plus or minus h bar over 2, h bar over 2, h bar over 2, plus or minus h bar over 2. Oh, sorry, I shouldn't be writing plus or minus. I should be writing minus or plus. The plus sign here, the top sign, going with the plus eigenvalue, since we end up with a minus sign here going back into this matrix, means we're going to have the opposite, minus plus instead of plus minus. So this matrix, multiplied by xy, equals 0, 0. This is equivalent to our original system if we substitute in the eigenvalue, either plus or minus h bar over 2. solving this system of equations, or just, doing the matrix vector product, means we end up with minus or plus h bar over 2x plus h bar over 2 y is equal to 0, or h bar over 2x plus, minus or plus h bar over 2y is equal to 0. Both of these equations, I can divide out the h bar over 2, both of these equations equivalently tell me that x is equal to plus or minus y. So this didn't actually solve to tell me what the eigenvectors are, but that's what you expect from an eigenvalue sort of system. The system of equations you're going to get here will always be singular, because we generated that system of equations by enforcing it to be singular, saying the determinant has to be equal to 0. So you have to use a little bit of intuition and cleverness to figure out what the solution is actually going to look like. X is plus or minus y, so I could write, for instance, that the eigenstate associated with the plus h bar over 2 eigenvalue is coming, again, with the plus sign now, is x equals y, or just something like 1, 1. That works, but that's not normalized. Let's run with that, actually. Let's say we substitute in x equals 1 and y equals 1. This is now for our h bar over 2 eigenvalue. When we normalize this, you're going to divide by the sum of the squares of both components, i.e. 2. We're going to divide by square root of 2. Our actual normalized eigenvector is going to be 1 over root 2, 1 over root 2. These 1 over root 2's are things that you see a lot when you're dealing with two-state quantum systems. And this guy, Griffiths calls this chi plus with a superscript x to signify that it is the eigenvector associated with the x component of the spin angular momentum with the plus sign in the eigenvalue. If we're working with the minus h bar over 2 eigenvalue, we're going to get the opposite signs here. So if I said 1 minus 1, well, I'm going to get something very similar when I normalize it. 1 over root 2 minus 1 over root 2. And Griffiths calls this chi minus with the superscript x. So these are our eigenvalues and eigenvectors for s sub x. What that means is that these are the states with definite x component of angular momentum. So this is a little bit strange. If I combine two states with definite z angular momentum in this very specific superposition, I end up with a state of definite x angular momentum. And depending on the sign of the superposition here, whether I add them together or subtract them from each other, the plus z component or the minus z component, the spin up case or the spin down case, if I say spin up plus spin down, I get plus spin in the x direction. If I say spin up minus spin down, I get minus spin in the x direction. It's a very strange sort of thing, but this is the fundamental weirdness of quantum mechanics. That's just how these things actually work in the real world. For instance, sequential measurements is the sort of thing that we can explain and understand reasonably easily from the perspective of the mathematics in the spin 1/2 case. Suppose I have some wave function, some state, and I don't know anything about the angular momentum associated with this, the spin angular momentum now. If I measure the z component of the angular momentum, you know what I'm going to get as a result of that. There are only two possible outcomes for a measurement of the z angular momentum. I could get h bar over 2 or minus h bar over 2. Suppose I get minus h bar over 2. If I take this state and I go to, say, measure the x component of the angular momentum now, I've measured s sub z and I've gotten minus h bar over 2. Back when we were talking about the generalized statistical interpretation of quantum mechanics, you know that after a measurement that gave you a particular eigenvalue of the Hermitian operator associated with the observable that you're measuring, the quantum state now is the quantum system now is in the state with the eigenvalue associated with that measurement. Essentially, the wave function collapsed. And since we're talking about a two-state wave function here, it's not necessarily a collapse of a wave function, but whereas what was originally potentially a superposition of up and down spins, we now know is in the down state. So we have the down state now, and we want to measure S sub x. We've prepared a quantum system in the down state. What are the possible outcomes for a measurement of S sub x? Well, the S sub x measurement could be, in principle, either h bar over 2 or minus h bar over 2. These are the possible outcomes, and we don't know necessarily which one is more likely yet. In order to figure out which one is more likely, you have to express this state, the ingoing state, as a superposition of the plus and minus eigenstates of S sub x. So the algebra problem we have to do to understand the outcomes of this second measurement is to express minus as a superposition of something times what Griffiths called chi plus x and chi minus x. In the algebraic notation, working in the basis of spin up and spin down, we know what the spin down state is. Very simple, 0, 1. We know what the eigenstates of the spin or S sub x operator are. We have 1 over root 2, 1 over root 2 for one of them, and 1 over root 2 minus 1 over root 2 for the other one. We're going to be combining these things together, and we want to make it equal here. What are these multipliers going to be? Well, you can see right away that if I add these two together, I can potentially get this term to cancel out. I don't want it to cancel out, so I'm going to have to be combining these things with a minus sign. If I multiply this one by 2 and this one by 1, if the numbers that I'm multiplying these guys by, they're what I'm going to replace the question marks with in this expression, if those things were unequal, I wouldn't get the top ones to completely nullify. The only remaining thing is that I need to normalize these things. And as before, what you should expect to see when you do normalizations like this is 1 over root 2's appearing. The 1 over root 2 in the probability context is going to get squared and become a half. So essentially this means that I have, if I prepare a quantum state in this system, or a quantum system in this state, I can treat it as an equal superposition of these two states, and an equal superposition properly normalized in the sense that I have to have something like down inner product with down equals 1, or writing this out, I have to have row vector 0, 1, complex conjugate, multiplied by column vector 0, 1, not complex conjugated. I have to have that equal to 1. That's okay. If I did that in terms of these states, you would find out that it actually works as well. So make sure everything's normalized, but keep in mind that we're only ever working with two states here, so we're only ever going to be superposing two things together. The superpositions don't have to be equal, of course, but I feel like I'm starting to ramble here, so I'm going to go back to the original problem and move on. We had a quantum state in an unknown system, measured the z component of the angular momentum, supposed that we got the minus h bar over 2 angular momentum eigenvalue, which meant that our quantum system was in the down z component of angular momentum eigenstate. And then in order to figure out the outcomes of a measurement of the x component of the angular momentum, we expressed that down quantum state as a superposition of eigenstates of the S sub x operator. This superposition then tells us that actually the down state is an equal superposition of the plus h bar over 2 and the minus h bar over 2 eigenstates associated with the S sub x operator. So actually, both of these are equally likely. This one is going to have a probability of 0.5. This one's going to have a probability of 0.5. So that's all well and good. It tells us what the outcomes of these measurements are. And this is something that hopefully doesn't surprise you too much, but should really have surprised you a lot when you first started to study quantum mechanics. I have a state, an unknown state. I measure the z component of the angular momentum. I determine it to be minus h bar over 2. Then I measure the x component of the angular momentum. and I find that it is going to be either h bar over 2 or minus h bar over 2. Knowing the angular momentum in the z direction didn't provide any information about the angular momentum in the x direction. What's really surprising about all of this is if I got this guy, if I observe minus h bar over 2, then I know the outcome of the measurement has essentially collapsed the wave function again, and it's collapsed it down into this state. So I know I'm working now with something that's 1 over root 2 minus 1 over root 2. This is my new quantum state. If I went back to measure s sub z again, I would have to re-express this as a superposition of up and down in order to find out what those outcomes would be. And you can probably see, given that up is just 1 here and 0 here, that I would have to write this guy as 1 over root 2 up minus 1 over root 2 down. Which tells me that we have an equal superposition of up and down, which means if we measure s sub z again, we would get either h bar over 2 or minus h bar over 2 with equal probability. So if we know nothing about our state, measure its z component to be down, then measure its x component to be negative, and then measure its z component again, we've forgotten about what the z component was. The measurement of x perturbed the system to the extent that we no longer had any information about the z component of the angular momentum. Mathematically speaking, this all boils down to manipulation of row and column vectors with only 2 components and 2x2 matrices. And 2x2 matrices are about as easy to work with as matrices ever get. So the spin 1/2 system is a very common test case for quantum mechanical systems. To check your understanding, I found the eigenvalues and eigenvectors of s sub x. I'd like you to go ahead and find the eigenvalues and eigenvectors of s sub y. And you can do that however you want. You can use Wolfram Alpha, you can use Sage, you can use Mathematica, use whatever you want. And then on the basis of knowing those eigenvalues and eigenvectors, suppose I prepare an eigenstate of the x component of spin angular momentum, and measure s sub y. What are the possible outcomes and their probabilities? Or, likewise, if I measure s sub z, what are the possible outcomes and their probabilities? One of the really nice features of the spin 1/2 quantum mechanical system is that while mathematically it's about as simple as quantum mechanical systems get, it can still be used to make predictions about the sorts of things that you could actually go and do in the lab with a moderate budget. Most of those experiments have to do with the behavior of spin 1/2 particles in a magnetic field, so let's see how that works exactly. The mathematical structure we're dealing with is the same as it has been for the past couple of lectures. We have 3 components of spin angular momentum: s sub x, s sub y, and s sub z. Expressed in terms of a basis of up and down. By up and down, I refer to the eigenvectors or eigenstates of the z component of angular momentum. These sx and sy and sz operators can be expressed as 2x2 matrices. These 2x2 matrices are usually written as the sigma x, sigma y, and sigma z Pauli matrices, which are essentially what you get if you remove an h bar over 2 from the matrix representation of the spin angular momentum operators. So we have these matrices. We know, for instance, the eigenstates of the s sub z operator. Since we're using those as our basis, we will have very simple expressions for the eigenvectors associated with the s sub z matrix operator. The eigenvalues, are h bar over 2 and minus h bar over 2, and the associated eigenvectors are 1, 0, and 0, 1. The expression of the eigenvectors and eigenvalues for sigma x and sigma y are slightly more complicated. The eigenvalue structure for x and y angular momentum is the same, of course, h bar over 2 and minus h bar over 2. But the eigenvectors are slightly more complicated. For the x component of angular momentum, and you can do this finding the eigenvectors by any algorithm involving 2x2 matrices you want, the math is not that difficult, you get 1 over root 2 pulled out front for normalization, 1, 1 for the eigenvector associated with the positive eigenvalue, and 1 minus 1 for the eigenvector associated with the negative eigenvalue. For the y component of spin angular momentum, we get something that looks somewhat similar. 1 over root 2, 1, and then I for the other component, and 1 over root 2, 1 minus I. So we have 1, 1, 1 minus 1, 1 I, 1 minus I, and then 1, 0, and 0, 1. These eigenvectors and eigenvalues tell us pretty much everything we need to know about the quantum mechanical mathematics of spin angular momentum. From the physics perspective, what's interesting about this is that particles with spin angular momentum typically have a magnetic dipole moment, mu, that is directly proportional to their spin angular momentum. So if we're working with a particle with spin angular momentum, the proportionality constant gamma here directly tells us the magnetic dipole moment. You can think about magnetic dipole moments classically relatively straightforwardly. Suppose we have a large sphere that contains some mass and contains some charge. I don't know exactly how the mass and how the charge is distributed, but if this is rotating, it will carry that charge around in a circle, and it will carry its mass around in a circle, and therefore it will have both angular momentum and a magnetic dipole moment coming from the equivalent circular current of the charges as they rotate. I can simplify this picture a little bit by pretending that I'm just working with a ring of charge, or a ring of mass, rotating about the z-axis at some angular frequency omega. If I want to know the angular momentum of a rotating ring of mass m, suppose it has radius r, and angular frequency of rotation omega, I can write that down fairly straightforwardly. It's the moment of inertia of a ring rotating about its axis, mr squared, times the angular frequency. The magnetic dipole moment, mu, can be expressed similarly. The magnetic dipole moment of a ring of current is given by the area of the ring times the current flowing in the ring. So, pi r squared times the current. If I suppose that I have some charged particle that's rotating around this ring, the angular rate of rotation of that particle being given by omega, I can express the current in terms of the overall frequency and the charge carried by that particle. My magnetic dipole moment then becomes pi r squared for the area of the ring times omega over 2 pi, the overall frequency, the number of times per second a charge passes, times the charge itself. So this is going to be a total amount of charge per second, or a current. Rewriting this slightly, I can express this as mr squared omega q over 2m, essentially factoring out the angular momentum and leaving this rearrangement of constants. This then I can express as q over 2m times the angular momentum. And since what we're talking about is the spin angular momentum, I'm not going to write this as capital L, I'm going to write it as capital S. One interesting thing, and this is entirely a side note, this comment and the next slide is a side note. It's conventional to write this magnetic dipole moment as q h bar over 2m times the spin angular momentum divided by h bar, where this quantity is called the Bohr magneton. I'm telling you about this because this expression doesn't actually work. This Bohr magneton, while it is in some sense a fundamental unit of magnetic dipole moment, does not actually give you the dipole moment of a spinning electron. We have to add a fudge factor, which is called g. The g factor gives you sort of a correction to the proportionality between spin angular momentum and magnetic dipole moment. The reason g is so interesting is that it's something that we can measure to exquisite accuracy in the lab. This is the current measurement of the g factor associated with the electron spin magnetic dipole moment. I told you this is an experimental number, this is a measurement, and the uncertainties on this experimental value are really only present in the last decimal places. The smallest this number can be is 0.7 in the last 2 decimal places, and the largest this number can be is 3.7 in the last 2 decimal places. So this is our experimental number. Let me put an exclamation point on that because this is really an astonishingly accurate measurement. If you look at this number, this 2 here signifies 2 parts per thousand, already a pretty good measurement. This 9 signifies parts per million. This 4, parts per billion. This 2, where the uncertainty first arrives, is at the parts per trillion level. So we're really accurate with experiment to better than a part in 10 to the 12th. Imagine counting something, and counting up to 1,000,000,000,000, and only being off by 1 or 2. That's really an astonishingly accurate number. Theory hasn't quite caught up, but it's actually doing astonishingly well. If you go into relativistic quantum mechanics, you will learn that electromagnetic interactions can be treated from a quantum mechanical perspective as well. So quantities like the magnetic field or the magnetic dipole moment can be treated from the perspective of quantum mechanics. Knowing that they can be treated from the perspective of quantum mechanics, you can actually make quantum mechanical calculations of fundamental physical properties like this G factor associated with the electron spin magnetic dipole moment. Theory can get us this far. The more accurate you want to make your theoretical calculation, the more cumbersome that calculation gets. Essentially, you're adding up terms in an infinite sum. And the more accurate you want your result to be, the further closer to infinity you have to get. Current theoretical calculations have been carried out to this, the parts per billion level, and it agrees exactly with the experimental observation. So this is really an astonishing success of quantum mechanics, relativistic quantum mechanics in particular. But all of this doesn't really have all that much bearing to the sorts of experiments that I'm going to be talking about, the behavior of spin 1/2 particles in magnetic fields. So, getting back to our particle in a magnetic field. One facet of particles in magnetic fields is that if you have a magnetic dipole moment, there will be a magnetic energy associated with the relative alignment of the dipole moment in the magnetic field. The energy is given by the dot product of the magnetic dipole moment vector and the magnetic field vector, and this is, in some sense, a purely classical value. To make this a little more concrete, let's express the magnetic field as B naught, and I'll just give it a direction. Let's say it's in the z direction. The dot product then of our magnetic dipole moment, which you know is going to be associated with the spin angular momentum then, since the magnetic field is only in the z direction, it will pull out only the z component of the magnetic dipole moment. So I'm going to have an S sub z in this expression for the energy. Now energy, you've seen that before in quantum mechanics. We know the energy operator is the Hamiltonian. So the Hamiltonian under these circumstances is given by minus gamma B0 S sub z, where gamma S sub z is the z component of the magnetic dipole moment, and B0 is the strength of the magnetic field. Now, this expression, and I'll put hats on it for now, this is really involving operators. So, reasoning by analogy from classical expressions, you can come up with quantum mechanical expressions, which may or may not work. Let's see what the implications of this expression for the Hamiltonian are. The Hamiltonian allows us to write a time-independent Schrödinger equation to find our stationary states. H psi equals E psi. Now, H psi is E psi. Well, we know what the Hamiltonian is now. We can substitute that in. Minus gamma B0 S sub z psi. If that's going to be equal to E psi, what we have here is an eigenvalue problem. Our operator is S sub z, our state psi, and our eigenvalue S sub z acting on psi is given by the eigenvalue minus E over gamma B0 psi. You know about the eigenvalue problem of S sub z, though. S sub z acting on some psi gave us plus or minus h bar over 2 times our eigenstate back, and we wrote our eigenstates as either plus or minus spin 1/2, either up or down. If I write this as up, I use the plus sign. If I write this as down, you use the minus sign. So we know about the eigenstates and the eigenvectors of the z component of angular momentum. That was what we used as a basis when we were expressing our Pauli spin matrices, for instance. What that allows you to do is identify the eigenvalues you get here with the energies. What that tells you is that the energy of, for instance, the spin up state is going to be minus gamma B0 h bar over 2, and the energy of the down state is going to be the opposite sign, gamma B0 h bar over 2. Our stationary states, therefore, are just going to be our spin up and our spin down states, the same sort of states that we've been working with over the past couple of lectures. The energies associated with these states are now different, since we are allowing them to interact with a magnetic field. if I have a magnetic field pointing upwards, the up angular momentum operator, the dot product of the up arrow with the up magnetic field is going to be a positive number, so we're going to have a negative magnetic energy corresponding to this minus sign here. So there's really no mystery here between or among these energies and the states that we're working with. Knowing the stationary states and their energies, of course, we can make an expression of time evolution. We've done this sort of thing before. The time evolution of some general state psi, given in terms of just some constant a and some constant b, where here I'm going to simplify things by saying a squared plus b squared equals 0. I'll simplify this even further, actually, by the simplification here is that I'm not allowing a and b to be complex. A and b are purely real. But that's just going to be a relative phase overall, which isn't going to change our results significantly. So I'm going to write a as, there's a little bit of guesswork involved here, but to simplify the notation, you can write this as cosine of alpha over 2, and b as sine alpha over 2. The reason to use trigonometric functions at this stage is simply to enforce normality, since sine squared plus cosine squared is going to be equal to 1, not 0. Why do I keep writing 0 for normalization? Normalization requires the sum of these squares to be 1, not 0, and our trig functions are simply enforcing that normalization. If I express up and down in their basis, the basis of up and down, you know this is going to be 1, 0, and this is going to be 0, 1. So I can write this overall. My psi of t, then, is going to be the time evolution of each of these states. A times the time evolution factor that we're familiar with. I'll write this as a up arrow times e to the minus I e up t over h bar plus b times down e to the minus I e down t over h bar. This is the same sort of time evolution expression we've been working with for a while now. If I work in this basis, this expression, the up and the down are going to be replaced by their column vectors, which are simple. So when we combine them, we're just going to end up with the cosine alpha over 2 from our assumption about the form of a times e to the I gamma b naught t over 2, since our h bars cancel out. Likewise, sine alpha over 2 e to the minus I gamma b0 t over 2 is our expression for the column vector evolving in time associated with a general superposition of up and down with amplitudes given by a and b. If this is our time evolution, what sort of properties do we expect our state to have, and how will those properties evolve with time? We've done calculations like this before, for instance. Let's calculate the expected value of the angular momentum components to see how they evolve with time. The result is something called Larmor precession, and you can see it, for instance, by calculating the expected value of s sub x. S sub x, expected value, you can write that as some psi of t, the state under which we're calculating the expectation, s sub x, psi of t. Psi of t now being given by this complex column vector, the Hermitian conjugate of psi of t is going to be a row vector, complex conjugated form of this. So I can write that as cosine of alpha over 2 e to the minus I gamma b0 t over 2. And I'll put a comma in here to signify the space between the two components of my row vector, sine alpha over 2 e to the I gamma b0 t over 2. Since this is an expression for the complex conjugate of this vector, I have to change the signs in the exponents here associated with the imaginary parts, which is why I've got a minus sign associated with my cosine term, whereas here I had a plus. Now we're evaluating an expression, the Hermitian conjugate of psi of t, on the left of the s sub x operator, to the left of psi of t. The s sub x operator, we know what that is expressed in this basis. It is given by h bar over 2, 0, 1, 1, 0. And then our psi of t is our column vector as before, cosine alpha over 2 e to the I gamma b0 t over 2, sine alpha over 2 e to the minus I gamma b0 t over 2. Doing the matrix vector product and then the vector vector product that results gives you something relatively straightforward. If you look at the structure of this, and I apologize for the messiness, hopefully it's still reasonably easy to see what all of these terms mean. The fact that the only non-zero entries in this matrix are the off-diagonal elements, what that is essentially going to do is swap the entries in this row vector. For instance, if you calculate the top entry of the row vector that results from this matrix vector product, it's going to be 0 times cosine, the cosine term, plus 1 times the sine term. So it's just going to be the sine term appearing in the top position. Likewise, we'll get the cosine term appearing in the bottom position. When I do the vector-vector product then, I'll end up with the cosine term from here associating with the sine term from here, the sine term from here associating with the cosine term from here. So both terms in my vector-vector product that results here are going to have a cosine sine in them, a cosine alpha over 2 times a sine alpha over 2. The complex exponentials combine in much the same way. I'm going to have a e to the minus something combining with an e to the minus something in multiplication, and an e to the plus something combining with an e to the plus something in multiplication. If you write that all out, and I'm skipping obviously a lot of steps of algebra here, our h bar over 2 carries out to the front, and we're going to get a cosine alpha over 2 sine alpha over 2 times, factoring that out since it's present in both terms, e to the minus I gamma b0 t. Since we have e to the I gamma b0 t over 2 multiplied by e to the minus I gamma b0 t over 2, the over 2's essentially cancel out when we add the exponents together. The other term is going to come in with a plus sign, e to the I gamma b0 t. Same form. You can probably tell what's going to happen now if you recognize cosine times sine from back in ye olden days when you were studying algebra and you were learning about trigonometric identities. That's why I had guessed alpha over 2 here. This is the double angle identity. What this means is that overall this is going to simplify down to h bar over 2 times the sine of alpha, and the expression here, if you expand out the complex exponential as a cosine plus an I sine, you'll find that the sines cancel out, and we're just going to be left with cosine of gamma b0 t. So this is our expression for the time evolution of the x component of the spin angular momentum. It's oscillating with time. If you calculate the expected value of s sub y, you get a very similar expression, very similar algebra, only you'll be using the y Pauli spin matrix instead of the x Pauli spin matrix. And you get h bar over 2 sine of alpha times the sine of this gamma b0 t. So you can see what's going on. You have some amplitude here, h bar over 2 sine alpha times cosine for the x component and sine for the y component. This is a rotation of the expectation value in the xy plane. If you calculate the expected value of s sub z, you get a relatively simple expression, h bar over 2, which I should really write as h bar over 2, not some unintelligible squiggle, cosine of alpha is what you get. So the algebra here is simply expressing your state in the basis, expressing your operator in the basis, taking appropriate Hermitian conjugates, complex conjugate transposes, and doing matrix vector multiplications. That's all that's necessary to calculate expectation values here. And what you get is precession at a frequency given by this gamma beta. So effectively we have a frequency gamma, sorry, it's not a beta, it's a b, gamma b0. This is Larmor precession. And what it looks like is if I had some coordinate system here, you can visualize this as having some spin angular momentum vector at some angle alpha from the z-axis and it's precessing around at a frequency omega given by this gamma beta 0. So the z component of this vector is remaining constant, and it's precessing around the z-axis. If you worked out what would happen for the case of a spinning charged ball in classical physics, you would find it actually has exactly the same behavior. This is expected because of some theorems in quantum mechanics that we studied earlier that tell you that the evolution of the expectation value obeys the classical behavior. So this is one sort of prediction, and this is the sort of thing that you can actually measure. The fact that this Larmor precession, incidentally, is at the base of what happens when you're making those extraordinarily precise measurements of that G factor I mentioned earlier. The Larmor precession frequency can be measured very accurately, and it's related to, of course, this gamma, which is associated with the, well, spin angular momentum. The other experiment that I want to mention is the Stern-Gerlach experiment, which is the result of another facet of the interaction of magnetic dipoles with magnetic fields. If your magnetic field is non-uniform, there is a magnetic force. This is the force that attracts two magnets together, and it stems essentially from the same sort of magnetic energy. The force, as derived from the energy, is given by the gradient of the energy, and we're talking about spatial gradients now. So your dot product of magnetic field, or magnetic dipole moment with magnetic field is an energy, and the gradient of the energy tells you how that energy changes as your magnetic dipole moves around spatially. So if there's a region of particularly strong magnetic field, it will be associated with a particularly high or particularly low energy. And the forces that result from that will tend to move the particle either towards or away from those regions of strong magnetic field, depending on the relative alignment. Either your magnets will attract or your magnets will repel. The reason this is important is that you can use this magnetic force to do quantum mechanical experiments. Suppose I have a magnet, and I'll draw it with, say, a north pole up here and a south pole down here. The reason the pole pieces are shaped the way they are under these circumstances when you're doing an experiment like this is you want to make a magnetic field that is non-uniform. When you have such a non-uniform magnetic field, you know you will be getting a magnetic force. Forces like this don't enter into quantum mechanics, however. The reason for that is if you think back to the Schrödinger equation, there was nowhere to put a force. The only thing that we could work with was potential. Well, we can work with potentials here. We can derive a potential associated with this force. And what that potential will do to particles with spin either up or down, which I'll write now as plus or minus, is it's going to change it from, instead of just being gamma b0, to minus or plus gamma b0 plus some alpha z. So instead of just having an energy associated with the magnetic field, we're now going to have an energy associated with the gradient of the magnetic field as encoded by this alpha parameter. The larger the gradient of the magnetic field, the larger the force, and you can think about the force here just simply resulting from a potential that varies in z. But it varies with z in such a way that the orientation of the dipole moment pardon me, the z component of the spin angular momentum enters into the energy expression. If you work out what the time evolution factors look like then, they look like something like e to the I e plus or minus t over h bar, as before. But since this energy now has some spatial variability in it, our energy time evolution factors end up looking like plus or minus I gamma t b naught over 2, same as before, and e to the plus or minus I alpha gamma t over 2, all multiplied by z, and I've forgotten an I in this exponent here. So the fact that there's some z dependence to our energy now means that there will be z dependence in our time evolution of energy. And if you compare, for instance, the fact that we have an e to the I k z here, essentially, this is going to look like an e to the I k z, plus or minus. This looks like z momentum. This is not an especially rigorous argument because I have not actually expressed the wave function as a function of both position and spin. Doing so makes this math a little bit more complicated. You can look in the textbook if you want a slightly more complete derivation here, but conceptually what you need to understand is that a spin oriented in the downwards direction is going to be deflected upwards in this magnetic field, since it's going to be essentially attracted to the regions of high magnetic field. Magnets that are aligned with each other attract, whereas a spin oriented upwards is going to be deflected downwards in this magnetic field. So if I have some unknown particle here, a particle with unknown angular momentum, and I send it into this magnetic field, quantum mechanics now tells us that it will be either deflected up or deflected down. If I have a particle detector here that I can move up or down, or if I have a sheet of film that will be activated when these particles hit it, I will see a blob here and a blob here when I repeat this experiment many, many, many times. The particle, as it enters this region of magnetic field gradient, experiences a force and picks up a momentum that is going to depend on the amount of time it spends in the region where the magnetic field has a gradient. You know quantum mechanically that the only allowed states of this z component of angular momentum are either up or down, essentially. So you're going to get a deflection either up or down. You might ask why I'm only talking about up or down here. Why not the x or y components of the angular momentum? Well, if you think back to the previous slide where we were talking about Larmor precession, you know if there's some x component of the angular momentum, it rotates around in the xy plane very rapidly. So essentially any net force you might experience due to x gradients of the magnetic field and x components of the angular momentum will very rapidly cancel each other out, since we're averaging over many, many, many cycles. The Larmor precession frequency is typically much higher than the amount of time it would take the particle to traverse this region of magnetic field gradient. So this experiment here, which is typically done with silver atoms, for instance, aggregate particle with a summed angular momentum equal to 1/2, such that we can treat it with the formalism we're using for the spin 1/2 system. As that silver atom, being neutral, traveling relatively straight through the magnetic field, it will only experience a deflection due to its magnetic dipole moment, which, as you know, being mu given by gamma s sub z, will obey the quantum mechanics of s sub z. We will only see two possible outcomes. So this Stern-Gerlach experiment gives us something that's deeply non-intuitive if what you are expecting is the classical physics result, which says that, well, we're going to have a random distribution of initial magnetic dipole moment vectors over here, and as they travel through, we're going to get essentially a broad distribution of positions, a broad variety of deflections of that magnetic dipole moment. This experiment was first done in 1922, and really was very important for kicking off the development of quantum mechanics. Quanta had been studied a lot before 1922, but this is before that famous picture that I showed you in the very first lecture in this course, the Solvay conference, that was taken more or less around when quantum mechanics was first developed. That was in 1926, 1927. So this is a very obvious experimental indication that something is very wrong with classical physics. And now we know how to explain it using the formalism of the spin 1/2 quantum mechanical system. To check your understanding of all of this, here are a couple of questions about what might happen to particles either spin up or spin down in various magnetic fields. You know a little bit about angular momentum now in quantum mechanics, in particular the spin 1/2 system and how it can be represented mathematically, how it behaves, how to analyze it. You also remember a little bit about the experiments that can be done to study, for instance, the spin 1/2 system. In the Stern-Gerlach experiment, for example, you have a magnetic field, a non-uniform magnetic field in particular, and if you shoot particles in from one side, they will either be deflected up or down, depending on whether they're spin up or spin down. I hand-waved terribly when I described the initial particles here, though. The initial particles, typically for the Stern-Gerlach experiment, are silver atoms. And silver atoms are not something that we know how to represent quantum mechanically. They're very complicated. There's lots of electrons, there's lots of protons, and lots of neutrons. How can something like that overall behave simply like a spin 1/2 system? That has to do with how angular momenta add together in quantum mechanics. I'm only going to be able to scratch the surface of addition of angular momentum. There's actually a lot of deep mathematics that goes in here, and you'll get a feel for some of that. But the simplest case, and what we're going to start with, is two spin 1/2 systems. Suppose I have two spin 1/2 systems, and I'd like to combine them together to find out the behavior of the total angular momentum, for instance. Spin 1/2 systems, you know how they behave. They're either going to be up or down. And if I'm going to have two spin 1/2 systems, I'm going to write that, for instance, as two arrows inside my ket. So up, or up, down, or whatever. The possibilities that we have, if we've got two up spins, two down spins, one up, one down, etc., are either up, down, up, or down, down. Just the two, or the four possibilities for either up or down. If you think about the total angular momentum of these states, what we're thinking about in the context of total angular momentum, let's think about just the z component of the total angular momentum of these combined particles. I'm going to write this as s sub z superscript 1 plus s sub z superscript 2 for z component of the angular momentum of the first arrow in this state, the first particle, and the z component of the angular momentum of the second particle. For instance, if I'm looking at the expected value of the angular momentum the angular momentum z component associated with this sum, I'm going to say s sub z applied to this. Well, the s sub z2 isn't going to do anything with this. It's only going to focus on this, whereas s sub z1 is going to focus on this. So what we're going to end up with for this would give us h bar over 2 minus h bar over 2 would give us 0 for the z component of the angular momentum associated with this state. You can make the same sort of argument for the other angular momenta for these other states. This one is going to give us a total z angular momentum of 1, this one 0, as we said, this one 0 as well, as we said, for pretty much obvious reasons. If this is going to be plus, this is going to be minus, summing to 0, then this being minus and this being plus, summing to 0 as well. Two downs gives us a minus 1. This is vaguely reminiscent of the angular momentum structure we had when we were working with spin 1, for instance. We have 1, we have 0, we have minus 1, but we actually have two zeros here, so something's not quite working out. The way to treat this mathematically is to consider lowering operator applied to this up state. Now, the lowering operator that I'm going to work with here, s minus, is going to be broken up in the same sort of way as this s sub z. So let's write this as s sub minus on 1 plus s sub minus on 2. Don't think this is s sub minus squared. This is s sub minus acting on the second particle in my combined quantum state. So if I actually do that, let's write it out. S sub minus 1 plus s sub minus 2 acting on my up quantum state. Well, s sub minus 1 is going to lower the first, s sub minus 2 is going to lower the second, but they're combined with the plus sign here. So what I'm going to end up with is going to be something like down up when I lower the first, plus up down when I lower the second. And if I want to properly normalize this, I'm going to need a 1 over root 2 outside to take care of half of this and half of this, essentially. So if I have up with total angular momentum, z component of angular momentum 1, and if I have these down up states, which I know have z component of angular momentum 0, what happens if I act my combined lowering operator on this state? Can I lower it once again and get minus 1? Indeed I can. If you think about what s minus 1 plus s minus 2, our combined lowering operator, acting on, I'll pull the 1 over root 2 out front, down up plus up down. If you think about what the lowering operator does to this, I'm going to have 4 separate terms when I make the distribution. An s minus applied to this and applied to this, and an s minus 2 applied to this and applied to this separately. But most of those terms end up being 0. If I apply s minus 1 to this state, the first particle here, the down arrow, is already in the lowest state that it can possibly be in. I can't lower a minus 1/2 any lower for this spin 1/2 system, which is what I'm working with. So this lowering operator applied to this is going to give me 0. Likewise, if I apply the lowering operator for 2 to the second state here, I'm going to get 0 as well, because I can't lower this second state any lower than it already is. Now if I apply the second lowering operator to the first state here, I'm going to convert this up into a down. And if I convert this, or apply this first lowering operator to the second state, I'm going to convert this up into a down. So the only thing I'm going to be left with is down, down. And properly normalizing things is just going to be left with as down, down. And if you calculate the total angular z component of angular momentum associated with this combined state, you find it has total z component of -1. So now we're talking. We have three states, 0, 1, and -1, z component of angular momentum. And this looks a lot like the total angular momentum of 1. So it looks like we're talking about a state Lm of 1, and then either +1, 0, or -1 for m. Typical angular momentum. A spin 1 state, if you want to think about it that way. These are not the only possible states that we can make by combining these things, though. Since we have essentially 4 distinct states here, we would expect there to be 4 distinct states here. And indeed, just by orthogonality arguments, you can construct yet another state, 1 over root 2, and let's call it down, up, minus up, down. If you calculate the z component of the angular momentum for this state, you'll find that it's 0. And if you actually try and calculate the raising and lowering operators applied to this state, you'll find that it doesn't work. The combinations that combined with the plus sign here to give me minus minus, when I lower both of these, are going to combine with a down down, are going to combine with a minus sign to give me 0. Essentially, if I try to apply the lowering operator to this state, for instance, lowering this gives me 0, lowering this gives me down, so I've got down down. Lowering this gives me down, lowering this gives me 0, so I'm only going to be left with down down. So I've got a down down minus down down. And the expansion overall is going to look very much like this, except instead of having a plus sign with the minus sign, you're going to get 0 when you apply the lowering operator. You're also going to get 0 when you apply the raising operator. So essentially, this state here looks like L and M of, let's say, 0 and 0. This looks like a spin 0 state. I can't raise or lower it to anything. These states are technically called the triplet and the singlet. So when I combine two spin 1/2 systems like this, I get a group of 3 states that acts like a quantum mechanical system with L equals 1, coupled with or combined with a quantum mechanical system with L equals 0. A little bit of notation here. If what I really want to do is combine 2 arbitrary quantum mechanical systems with spin up and spin down, spin S1 and S2, the possible quantum mechanical systems that I'm working with as a start in terms of the spin is I've got a quantum mechanical system with spin S1 and z component quantum number M1, and a quantum mechanical system with spin S2 and z component quantum number M2. So I really have a system that can best be described by S1, M1, S2, M2. If I want to determine the total angular momentum, whereas for spin 1/2 systems I got a triplet and a singlet, a spin 1 system and a spin 0 system, what I can actually get out of this is combined quantum mechanical systems with total angular momentum S1 plus S2, and then some quantum number associated with that, M, being somewhere between S minus S1 plus S2 and plus S1 plus S2. This is an S2 here. I can also make quantum mechanical combinations with S1 plus S2 minus 1 for the total angular momentum, and some associated M for that as well. I can continue as well also S1 plus S2 minus 2 if I have enough angular momentum for that. The structure that I'm trying to get at here is that if I have 2 angular momenta two arbitrary spins, S1 and S2, I can make a variety of quantum mechanical states. In the case of S1 and S2 equaling a half, I could make a triplet state with total z component, maximum z component value 1, which gave me 1, 0, and minus 1 allowed values for m, and a singlet state with 0 for the total angular momentum and only one allowable state there. As an example, suppose I want to combine a spin 3/2 quantum mechanical system with a spin 1 quantum mechanical system. You know your 3/2 quantum mechanical system has allowable z components of angular momentum 3/2, plus 1/2, minus 1/2, and minus 3/2 for a total of 4 states, whereas your spin 1 quantum mechanical system has allowed z components of 1, 0, and minus 1, 3 states. With this formalism here, you can convert the combination into a spin 3/2 plus 1, or into a spin 5/2 quantum mechanical state. 5/2, if that's the total angular momentum, the z component of your total angular momentum is going to be 5/2, or 3/2, or 1/2, or minus 1/2, minus 3/2, or minus 5/2. So you actually have 6 states here. Or you can make a 3/2 quantum mechanical system with 4 states. Or you can make a 1/2 total angular momentum quantum mechanical system with, well, 2 states. So when I'm combining a spin 3/2 system and a spin 1/2 system, it's not just going to be a triplet and a singlet. I'm going to get a 5/2, or a 3/2, or a 1/2, depending on how I make superpositions of these quantum mechanical systems. Overall, however, you'll notice that if I have 4 states and 3 states, and I'm combining them independently, I'm going to end up with 12 states total, 3 times 4. Whereas, if I'm combining these states, these are independent, but they're not independent in a multiplicative sense. They're independent in an additive sense. I can make 6 different states with this, 4 with this total, and 2 with this total. And if I add those up, you're going to get 12 states again. So the total number of states doesn't matter, whether you're expressing it in terms of total L and total M, or S1 and S2. The actual way in which you calculate how to express superpositions of S1 and S2 in terms of L and M involves something called Clebsch-Gordan coefficients, and they're bloody complicated. This is a page from the particle data group, which is a group of particle physicists which come up with sort of internationally accepted values for physical constants, for instance, like that G factor number. You could go to their website and look it up. They also provide a lot of really nice documentation, including this, which is a page from one of their quick reference guides. And the Clebsch-Gordan coefficients essentially allow you to calculate superpositions in terms of L and M, in terms of S1 and S2 states. For instance, we just talked about the superposition of spin 1/2 quantum mechanical system with spin 1/2. So I'm sorry, not superposing, I'm combining 2 spin 1/2 systems. The notation here, M1 and M2, are then going to be the z component quantum numbers associated with spin 1/2 and spin 1/2. Whereas what they're calling J and M, those are quantum numbers associated with the combination, the combined angular momentum. So, for instance, spin 1/2, plus 1/2, and plus 1/2. This is essentially up and up. Up and up can combine to make a J, or total angular momentum, plus 1, and have a z component, plus 1, in only one way. Essentially what this is telling you, this 1 here, it's telling you that up, up is equal to essentially 1, 1 in this JM context. So S1 being up, S2 being up, is equivalent to L and M both being 1. Now the numbers here are difficult to read because a square root sign is to be understood over every coefficient. For example, minus 8/15 should be read as minus 8/15 inside a square root. So the minus sign is outside and the square root is assumed. So for instance, if what I want to do is determine the behavior of the state Lm is 1, 0, I want to write that as a superposition of S1, S2 sort of states. What I'm actually looking at is the 1, 0 L values. So I'm looking at this column here. So if I'm looking for 1, 0, I go for the 1, 0 in the superposition or combination that I'm interested in, and it tells me 1 half, 1 half, but they have the same sign. So what that tells me is that 1, 0 is going to be equal to 1 over root 2 for the assumed square root times up, up, which is what you get, sorry, not up, up. You have to look at the actual values of the table, Brent. So I'm going to have a 1 over root 2 and a 1 over root 2, and they're going to be combined with a plus sign. And the two states for m1 and m2 that are relevant are plus 1 half, minus 1 half, and minus 1 half, plus 1 half. So I'm working with essentially up, down, and down, up for our quantum mechanical allowed states. So what this tells you is that the L equals 1, M equals 0 combined quantum mechanical state can be expressed as a superposition, an equal and same signed superposition of the up, down, and down, up spin quantum number states, S1 and S2. You can do more complicated examples. For instance, suppose I'm interested in expressing in a combination of spin 1 and spin 1 half, a combined spin 1 half quantum mechanical system. If what I'm interested in then is, for instance, the 3 halves minus 1 half total angular momentum state, as a result of superposition of 1 and a half spin quantum states, I'm looking at these quantum numbers, these Clebsch-Gordan coefficients, 2/3 and 1/3. What that tells you then is that L and M of 3 halves minus 1 half can be expressed as a superposition of 0 minus 1 half. So I'm going to have to write a new notation here. Let's say 0 down for 0 minus 1 half, and minus 1 plus a half, minus 1 up. So 0 down and minus 1 up both contribute to a 3 halves total combined angular momentum minus 1 half z component combined angular momentum. And they add together not equally in this case, but with 2/3 and 1/3, which means I'm going to have to say root 2 over 3 and plus, since there's no minus signs in this column, 1 root 1 over 3. So the notation here is complicated, and this is not something that we're going to be using a lot of, but this gives you a feel for the rich mathematical structure of combinations of angular momentum. This page, actually, I cut it off here. It goes down for substantially higher orders. And, you know, characteristic of physicists always trying to be efficient, they've crammed definitions of the spherical harmonics into the gaps in between this rather stylistically described table. The moral of the story here is that if you want to express a combined angular momentum state in terms of the components that are being combined together, you can do so by looking up the numbers in this table, applying suitable minuses and pluses and square roots to get the overall definitions. Your textbook has a compressed version of this table, but yes, at any rate, this shows some of the rich mathematical structure. Now, in the words of your textbook, if you think this is starting to sound like mystical numerology, what we're really talking about is the decomposition of the direct product of two irreducible representations of the rotation group into a direct sum of irreducible representations. You can quote that too to impress your friends. This is not me, this is Griffiths. And mystical numerology is really not that far from the truth. The question is, why does math work so damn well when it comes to quantum mechanics? Really, for instance, the origin of all of this is the relationship between symmetries and conservation laws. That's something called Noether's theorem, and I alluded to it in class a while ago. What Noether's theorem tells us is that whenever there is a symmetry in physics, that implies a conservation law. For instance, what we've been talking about, conservation of momentum, we have some conserved L. That is equivalent to, or arises from, depending on your point of view, rotation symmetry. The fact that we can rotate our coordinate system however we want and not change the fundamental expressions of the laws of physics means we're going to have a conserved angular momentum. When it comes to the mathematical side, rotations form a group. Group theory then enters the picture. The mathematics of the rotation group is very rich. In particular, the rotation group that we're working with is called SO3 in mathematical notation, for the special orthogonal group in 3 dimensions, in this case. And, well, you can do lots of math with groups. In particular, groups have representations. And you can think about a representation of a group essentially as a set of matrices that obeys the same structure as the group that you're representing. And, well, representations of groups have their own mathematics associated with them. For instance, you can talk about irreducible representations or direct products of irreducible representations. But there's a whole lot of math going on behind the scenes here in the construction of a table of Clebsch-Gordan coefficients. And this very deep mathematical and physical connection between symmetries and conservation laws, and the mathematics of symmetries, the group theories of symmetries, in particular the rotation group and the representations of the rotation group in terms of matrices, are essentially what give us angular momentum in quantum mechanics. The mathematics of angular momentum in quantum mechanics is essentially the mathematics of representations of the rotation group. So there's a lot of complicated math going on behind the scenes, but those are some sentences, in particular things that maybe will impress your friends if you tell them that you're learning about group theory and applying it to physics. At this level, there's not much more that I can tell you about group theory, not because there isn't much more to group theory that's relevant to what we're talking about, but because it's been so long since I studied it. I did actually go and dig up my Representations of Finite and Compact Groups textbook and dig through to try and figure out if there was some nice tidbit that I could condense down. But, well, reading math textbooks isn't any fun. So that's all you're going to get from me on this topic. Perhaps suffice it to say that the math actually does work, and there are very deep, very elegant connections between symmetries, conservation laws, rotation groups, and angular momentum. To check your understanding of all of this, here are some calculations that you can do. These just involve looking up numbers in the table of Clebsch-Gordan coefficients. Now, if you're combining a spin 1 system and a spin 1/2 system, you're going to be looking at that 1 times a half entries in the Clebsch-Gordan coefficient table. It might actually write it as 1/2 times 1, I'm not sure. But you're going to be looking at that subtable. And I call these LM combined states. If L and M is going to be 1/2, 1/2, you're going to be looking at what in the particle data group Clebsch-Gordan coefficients is the JM column of 1/2, 1/2. And the corresponding rows are going to be these M1 and M2 values. And the coefficients that multiply the M1 and M2 values that appear in the corresponding rows are going to be the square root of the numbers, with minus signs moved outside as appropriate. So here are 2 sample superpositions for you to look up in the table of Clebsch-Gordan coefficients. Overall, what I really want you to take home from all of this is that angular momenta can be combined. The mathematics is complicated, and typically involves either doing some high-powered group theory or, for our purposes, looking numbers up in a table.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.